They say nothing escapes a black hole, not light, not matter, not even information. But what if black holes, as we've imagined them, are not quite real? What if they're illusions born of time's strange behavior near gravity's edge? There's a possibility, buried deep within general relativity, that collapsing stars never actually become black holes from our perspective. Instead, they become frozen stars, cosmic objects caught in an endless moment, stretching time so profoundly that collapse itself grinds to a visible halt. This isn't just a tweak to our models, it's a radical reimagining of what happens when stars die. It might even be the key to one of physics' greatest puzzles, the information paradox. But before we continue, subscribe to the channel so you don't miss out on any of these videos. The black hole, as introduced by general relativity, is a region of space where gravity is so strong that nothing, not even light, can escape its pull. At its core, according to the traditional view, lies a singularity, a point of infinite density, where space and time cease to exist in any meaningful way. But infinities make physicists uncomfortable. They're signals that our theories are breaking down. And perhaps nowhere is this breakdown more glaring than in the information paradox. If a black hole truly contains a singularity, and if information falls into it, never to return, then the laws of quantum mechanics, which require that information is preserved, are violated. That contradiction has haunted theoretical physics for decades. But maybe we've misunderstood the very nature of the collapse. To an outside observer, time near the event horizon of a black hole slows dramatically. As an object falls in, it appears to freeze just above the horizon. This is not just an illusion, it's a consequence of how space-time is warped by gravity. So what if, instead of thinking of black holes as singularities hidden behind event horizons, we considered the possibility that they're eternally collapsing objects that never finish collapsing? In this framework, dubbed the frozen star hypothesis, the formation of a black hole is never truly completed from the viewpoint of a distant observer. Time dilation becomes so extreme that the infalling matter asymptotically approaches the event horizon but never crosses it. This idea has deep roots in the original work of Oppenheimer and Snyder in 1939. When they first calculated what would happen to a massive star at the end of its life, their equations showed that, from the outside, the collapsing star would appear to freeze as it approached its Schwarzschild radius, the distance at which its escape velocity equals the speed of light. This wasn't a trick of perception, it was a legitimate consequence of Einstein's equations. Yet over time, physicists shifted the focus toward the experience of the infalling object, which does cross the horizon in finite proper time. But this shift in perspective may have obscured something critical. The outside view is the one we, as distant observers, can actually verify. So what do we really see in the sky? When we observe black hole candidates, what we're seeing are accretion disks, hot, glowing matter swirling around invisible centers. We're not seeing singularities. We're not even seeing horizons. The observable evidence is entirely consistent with ultra-compact objects that are merely very close to forming an event horizon. If they're frozen stars, the observational differences would be subtle, perhaps undetectable with current instruments. But why does this idea matter? Because if matter never actually crosses the event horizon from our frame of reference, then perhaps information isn't lost. Perhaps it remains encoded in the frozen shell of collapsing matter, visible in principle though inaccessible in practice. Hawking radiation, the theoretical quantum emission predicted by Stephen Hawking in 1974, might then not signify the loss of information, but rather its slow release over unimaginable timescales. This reframing could resolve the information paradox not by modifying quantum theory or inventing exotic new physics, but by rethinking what collapse really means. Quantum mechanics and general relativity are famously incompatible in certain regimes, especially where singularities are concerned. Attempts to unify them, like string theory and loop quantum gravity, often introduce mind-bending concepts like extra dimensions or quantized spacetime. But the frozen star hypothesis requires none of these. It stays within the framework of Einstein's relativity, using its own predictions about time dilation to challenge the notion of completed collapse. If nothing ever actually disappears behind a horizon, then we might not need to quantize gravity at all to explain black holes. They're not holes. They're frozen moments. Critically, this perspective shifts how we think about causality and observation. The traditional black hole model assumes a kind of omniscient view of the universe, where we can reason about what happens inside the horizon as if it's physically meaningful to do so. But in physics, what's observable often matters more than what's theoretically inferred. From our vantage point, the collapsing star never becomes a true black hole. Instead, it becomes a gravitational shell, growing increasingly redshifted and dim, but always present. If this shell holds the information, then Hawking radiation may simply reflect it in a scrambled, slowly evaporating form. This would mean that black holes are only black because of extreme time dilation and redshift, not because they truly enclose a region from which nothing can return. And while the proper time of the collapsing matter might be finite, that proper time becomes irrelevant to outside observers after a certain point. What matters is what we can detect, measure, and describe from a consistent external frame. The implications of this are enormous. Consider entropy. Black holes have entropy proportional to the area of their event horizon, not their volume, a strange fact that has led to the development of the holographic principle, suggesting the universe might be describable as a 2D surface projecting a 3D reality. But if black holes are actually frozen stars, perhaps the entropy is not stored behind a mysterious horizon but on the surface itself, the shell of collapsing matter. This could align with quantum expectations without invoking any new physics. Furthermore, this model allows for the possibility that information is not only preserved but may, in principle, be recoverable, though not practically accessible due to the enormous redshift. As the frozen star slowly evaporates through Hawking radiation, the information could leak out encoded in the quantum state of the emitted particles. This maintains unitarity, the cornerstone of quantum mechanics, without requiring information to escape from beyond a horizon. Another advantage of the frozen star picture is that it avoids the problematic notion of singularities. Singularities aren't just ends, they're points where the known laws of physics stop working. They produce infinities in equations, making predictions impossible. If no singularity ever actually forms, because collapse is never completed, then perhaps the universe avoids these unphysical conditions entirely. The mathematical divergence never manifests in reality. Of course, there are criticisms of this view. Some argue that the frozen star idea is a semantic sleight of hand, that from the infalling object's perspective, the collapse is complete, so it doesn't matter what distant observers see. But physics, especially in general relativity, is deeply tied to the frame of reference. If no signal can ever emerge from beyond the surface of the star, and if we can never confirm that an event horizon has formed, then perhaps that surface is all there is. There's also the issue of stability. Could such an object remain static or slowly evaporating over cosmic timescales without collapsing fully? Some theoretical models suggest it's possible. Others propose that quantum effects near the would-be event horizon might generate pressure or repulsion strong enough to halt collapse. These ideas are still being explored, but they suggest that frozen stars might be more than mathematical curiosities. What would it take to prove or disprove this model? Observationally, it's extremely difficult. The differences between a true black hole and a frozen star may lie just beyond our current detection capabilities. But as instruments like the Event Horizon Telescope become more precise, and as we study the fine details of gravitational wave signals from merging compact objects, we might find subtle clues, deviations from predictions that hint at a surface, a remnant, a frozen shell instead of a perfect vacuum. And what about the psychological implications? We often imagine black holes as terrifying cosmic traps, erasing anything that ventures too close. But the frozen star picture is more nuanced. It suggests that nothing is ever truly lost, only hidden behind the veils of time. It hints at a universe where information is sacred and conserved, where gravity doesn't destroy but only suspends. This view also invites philosophical reflection. If time can stretch to infinity at a boundary, if collapse can be frozen forever from our perspective, what does that say about the nature of time itself? Is time a universal constant or a local phenomenon, warped by mass and motion? And if so, how much of what we call reality is just a function of perspective. In many ways, the frozen star hypothesis is less about replacing black holes and more about reframing them. It keeps the gravity, the collapse, the intense redshift, but reinterprets what all of that means observationally and physically. It offers a conservative yet radical alternative, one that doesn't abandon general relativity, but reads it more literally. If the equations tell us that collapsing matter appears to freeze forever, maybe we should believe them. As we continue unraveling the idea of frozen stars, it becomes clear that this is not just an exotic theory tucked away in the margins of physics. It strikes at the very core of how we interpret space, time, and the fate of information in our universe. The deeper we explore, the more it becomes evident that the concept of an event horizon might be less of a physical boundary and more of a mathematical horizon created by the limits of our observation. If time truly dilates to infinity at this edge, then the collapse of matter doesn't complete from our vantage point, and what we call a black hole might be something far more subtle, a permanent optical illusion created by gravity's grip on time. This perspective brings into question one of the most foundational assumptions in black hole physics, that the event horizon is something real, absolute, and causally impenetrable. But if an external observer can never see matter crossing it, and if that crossing is an event that takes infinite time in their frame, then maybe the horizon isn't something that truly exists in a global sense. Instead, it may be a sort of epistemic limit, a point beyond which information cannot reach us, not because it has disappeared, but because it's moving too slowly through a stretched space-time fabric to ever arrive. Let's consider light emitted from a collapsing star as it nears its Schwarzschild radius. Each photon has to climb out of a deeper and deeper gravitational well. It becomes redshifted, stretched to longer and longer wavelengths, until it eventually becomes undetectable. But crucially, it never stops existing. It just becomes more and more difficult to detect. And this is a central pillar of the frozen star idea. Information isn't destroyed, it's redshifted into near invisibility. In principle, it's still there. In practice, it's locked behind an impenetrable curtain of time. This leads us directly into the heart of the black hole information paradox. If matter disappears into a singularity and an event horizon forms, then the information about that matter is seemingly lost forever. But according to quantum mechanics, information cannot be destroyed. Even if it's scrambled or transformed, it must be preserved. The frozen star model neatly sidesteps this conflict. There is no true horizon, no actual singularity, just a surface of collapse that never finishes falling. The information remains imprinted on the boundary, slowly radiating out over time in a highly redshifted, perhaps entangled, manner. Some physicists argue that Hawking radiation, if it truly exists, must carry this information back out. But in traditional black hole models, Hawking radiation is thermal, featureless, lacking any imprint of what formed the black hole. This is where firewall hypotheses, holographic principles, and black hole complementarity have been introduced. They attempt to patch the paradox, often by invoking radically new physics. Frozen stars, however, suggest a simpler solution. Hawking radiation might not emerge from a vacuum near an abstract event horizon, but from quantum fluctuations interacting with the still-present surface of the star. This surface might radiate in a way that allows information to leak out in a highly disguised but ultimately recoverable form. We can draw an analogy to objects falling into the sun. From their own perspective, they cross the solar surface in a finite time. But from our perspective, we see a trajectory, an approach, a disappearance, never the full event. Now amplify that by the warping of spacetime near an ultradense mass, and what you get is an infinite approach to a threshold that is never crossed in any measurable way. That's the nature of a frozen star. It approaches black hole status, but from the universe's point of view, it never completes the journey. Consider how this might impact gravitational wave astronomy. In a typical black hole merger, we expect the gravitational waves to follow a distinct signature, the chirp, the ring down, and so on. But if two frozen stars were to merge, might the resulting waveform differ slightly due to the presence of physical surfaces? Some theorists have predicted that if surfaces exist, they might produce faint echoes after the main gravitational wave signal. tiny ripples of rebounding energy not accounted for in standard models. Detecting these echoes would be incredibly difficult, but not impossible. As our instruments grow more sensitive, perhaps we'll find just such an anomaly, proof of surfaces where none were expected. Then there's the thermodynamic question. The entropy of black holes is a strange beast. According to the Bekenstein-Hawking formula, a black hole's entropy is proportional not to its volume, but to the area of its event horizon. This flies in the face of conventional thermodynamics, where entropy usually scales with volume. The holographic principle, developed largely from black hole thermodynamics, suggests that all the information in a volume of space can be encoded on its boundary surface. If frozen stars are real, this might be more than a mathematical trick, it could be a literal description. The information is stored on the surface of the collapsing object, whose area defines the capacity for encoding data. And what about the firewalls? Those hypothetical walls of high-energy radiation that might exist at the event horizon if quantum mechanics is to be preserved. The firewall proposal was born out of trying to reconcile the smooth passage across the horizon predicted by general relativity with the strict demands of quantum information theory. But in the frozen star model, there is no horizon to cross. There's just a gradually slowing descent, never reaching the bottom. No contradiction arises, and no firewall is needed. The paradox evaporates because the setup that caused it was never completed in the first place. Critics might point out that this idea privileges the view of an external observer. After all, from the viewpoint of someone falling in with the star, the collapse completes in finite time. They cross the would-be event horizon and move inexorably toward the singularity. So, which perspective is real? In general relativity, both are valid in their own frames. But in physics, what we can verify, observe, and measure carries tremendous weight. If no external observer can ever confirm that an event horizon has truly formed, if the observational consequences are functionally identical to a perpetually collapsing object, then the frozen view might be more physical than the fallen one. This also brings us to the concept of coordinate time versus proper time. Proper time is the time experienced by an object in free fall. It ticks along at the rate of the object's own clock. Coordinate time, on the other hand, is what distant observers use to measure events. It's tied to the gravitational field, the warping of space, the dilation of time. For the collapsing star, proper time might suggest that the end comes quickly. But coordinate time, the only kind available to the outside universe, tells a different story. The end never arrives. It's a philosophical as well as physical difference. Do we trust the time of the infalling matter, or the time of the observers outside it? In a universe where no one can ever see the collapse complete, the argument for trusting the external view becomes stronger. In some ways, the frozen star model recenters physics on the observable, on the empirically grounded, and turns away from hypothetical interiors that can never be accessed or verified. It also offers a cleaner interface with quantum theory. The universe, at its deepest level, is not continuous but quantized. Perhaps gravity is too. If frozen stars do exist, their surfaces might be composed of quantized spacetime elements, Planck scale, pixels, of geometry that encode all the information of the matter inside. These surfaces might pulse with fluctuations, radiate subtle quantum signatures, and dissolve not in a singularity but in a quantum fade-out, an evaporation that takes eons, but preserves every bit of data. There's also a haunting poetic quality to the frozen star idea. Stars live for billions of years, forging the elements that make up planets, life, and consciousness. When they die, they collapse, not into disappearance, but into silence. A silence so deep and stretched that it lasts forever. The star doesn't vanish. It lingers in spacetime's pause, redshifted and dim, but present. Not gone. Just beyond reach. From the perspective of future civilizations, perhaps these frozen relics will tell a different story than black holes. Maybe we'll learn how to extract echoes from their surfaces, to decode the slowed-down signatures of matter long collapsed. Perhaps they'll become keys to quantum gravity, fossils of time's strangest behavior, clues to the unification of the macroscopic and the microscopic. We should also note that frozen stars don't require exotic matter or modifications to relativity. They don't demand new forces or hidden dimensions. They arise naturally from Einstein's equations, if we take them seriously in the regime of strong gravity, and remember that observation is constrained by light speed and spacetime curvature. They're not fantasy. They're a reinterpretation, and perhaps a more consistent one, of the physics we already know. And this idea returns us to a more humble view of the cosmos. Black holes, with their singularities and mysteries, often feel like errors in the universe, tears in the fabric, contradictions in the code. But frozen stars feel different. They don't break the laws, they stretch them. They don't destroy information, they hide it. And maybe, just maybe, they hold the answer to reconciling the great conflict at the heart of physics, that between the deterministic smoothness of relativity and the probabilistic discreteness of quantum mechanics. If frozen stars do, in fact, represent the true outcome of gravitational collapse, then our entire conception of what lies at the heart of the universe's darkest objects must be rethought. Instead of treating black holes as regions where physics fails and singularities reign, we can begin to explore a more palatable and elegant picture, one where the rules still hold, albeit stretched to extremes. In this framework, nothing needs to be discarded or overhauled. We don't need to reject relativity or rebuild quantum mechanics from the ground up. We only need to listen carefully to the predictions already nestled in the equations and recognize that the truth may have been there all along, overlooked in favor of more exotic interpretations. This more conservative alternative, based solely on a rigorous reapplication of general relativity, brings a sense of continuity back into physics. Singularities represent disjunctions in our understanding, points where the curvature of spacetime becomes infinite, where density becomes undefined, where our mathematical descriptions collapse along with the object they aim to describe. But in the frozen star model, such singularities never manifest in the observable universe. They're confined to the mathematical limits of proper time and never realized within the observational frame. Instead, what we get is continuity, an object that approaches a critical state, slows down, and then simply stays. Timeless. Eternal. Now, let's examine the theoretical foundations a bit more deeply. One of the most profound concepts in general relativity is the warping of spacetime by mass. Near a massive object, time slows down. This is not just a metaphor, it's a measurable effect. GPS satellites, for instance, must correct for both the speed of their orbit and the gravitational field of Earth. The deeper a clock is in a gravitational well, the slower it ticks. Near a collapsing star, this time dilation becomes extreme. At the Schwarzschild radius, the time dilation becomes infinite, at least from the perspective of a distant observer. This is the very foundation upon which the frozen star model stands. If time truly grinds to a halt at the Schwarzschild radius from our external viewpoint, then anything that falls inward will appear to us as frozen just above the horizon. Not moving. Not collapsing. Just hanging in stasis, like a ghost image imprinted on the fabric of spacetime. The light it emits is stretched into invisibility, its surface fades away, but the information, the quantum fingerprint of everything that fell in, is still there. Still present. And still bound by the laws of physics. This leads us naturally into the realm of quantum field theory in curved spacetime. Hawking's famous calculation of radiation from black holes doesn't require a singularity. It only requires a horizon and a quantum field. If the collapsing object never actually forms an event horizon, but asymptotically approaches it, then the Hawking radiation could still occur. But now with a crucial twist, the surface of the star might influence that radiation. It might leave subtle quantum signatures, hints of structure, correlations, entanglements, tiny signals that information is not only preserved but still reachable in theory. Such ideas are already being explored under the concept of black hole mimickers. These are objects that look like black holes from a distance but differ at extremely small scales. Gravistars, fuzzballs, and Planck stars all fit into this family. Frozen stars join their ranks but do so without invoking speculative physics. They stick closely to what we already know, only reinterpreted through a different observational lens. If future observations of gravitational waves, for example, reveal after ring-down echoes or deviations from the predicted signal, this could be evidence not of black holes, but of objects with surfaces, frozen stars, still radiating, still echoing with the information they contain. Let us also consider the cosmic scale. The universe is filled with mysterious dark matter, an invisible substance that interacts gravitationally but not electromagnetically. Could some portion of this dark matter actually consist of these frozen stars, ancient remnants of collapsed matter that never quite became black holes? It's a possibility not easily dismissed. While traditional black holes are detectable through their interactions with nearby matter, frozen stars, with their muted emissions and no true horizon, might hide more quietly. Their gravitational influence would be the same, but they'd lack the finality of true black holes. Could the universe be hiding countless such objects, frozen in time, masquerading as the dark skeleton of galaxies? This idea also reverberates through our understanding of time itself. Time is not an absolute backdrop against which events unfold. It's a dynamic quantity, shaped by mass, motion, and energy. The fact that collapse can be arrested, at least from our perspective, by the warping of time suggests that time is not just relative, it's malleable. It bends, stretches, and can even freeze. The implications are staggering. Could there be other regions in the universe where time has essentially stopped? Could this be a mechanism through which nature preserves information, halting entropy, storing data and suspended animation? If we extrapolate further, this could have implications for cosmology. Perhaps the early universe, under extreme densities, created regions that never fully expanded or collapsed. Miniature frozen stars. Quantum seeds. Remnants of prior cycles. If the universe itself is subject to cycles of collapse and rebirth, perhaps frozen states play a role in preserving continuity. Cosmic hard drives carrying forward the blueprint of each cosmic epoch. The elegance of the frozen star model also lies in its predictive modesty. It doesn't claim to solve every problem. It doesn't overthrow established theories. It simply urges us to look again at what general relativity actually tells us, and to consider the real consequences of infinite time dilation. It asks us to reconcile our theories not just with one another, but with what can actually be seen, measured, and known. And that's a powerful scientific approach, to prefer models that don't break the observable universe in order to save the unobservable one. Critics of the frozen star idea often return to the problem of the infalling observer. They argue that since, in proper time, the horizon is crossed in finite time, the black hole must truly form. But again, we return to the issue of what is observable. From the external frame, the horizon never forms. And in relativity, that frame is as real as any other. More importantly, it's the only one from which we can perform measurements. If two observers disagree on an event, and only one of them can ever communicate the result, whose reality carries more weight? This brings us into the philosophical terrain of operationalism, the idea that the meaning of a concept lies in the operations used to measure it. If the formation of an event horizon is something no one can ever verify, if it's a feature that only exists in unreachable frames, then maybe it doesn't belong in our physical ontology at all. Maybe it's a mathematical ghost, not a physical entity. Frozen stars also make testable predictions, at least in theory. Their surfaces may reflect some of the infalling radiation or particles, creating interference patterns that differ subtly from those of true black holes. Over long periods, their evaporation might proceed differently, preserving quantum correlations that would otherwise be erased. Instruments that can detect high-frequency gravitational waves or minute fluctuations in gamma-ray bursts might one day see hints of these differences. There's also a fascinating possibility that frozen stars might be more common in the early universe. Back then, the density of matter was greater, the rate of star formation higher, and the gravitational interactions more chaotic. If any objects ever skirted the edge of becoming black holes but stopped just short, frozen in time, they might still be lurking today, dim, cold, and barely detectable. Future surveys of microlensing events, star movements, and gravitational anomalies might one day uncover them. And what about the end of the universe? If cosmic expansion eventually slows, halts, or reverses, massive structures might begin collapsing again. If enough mass collects into a region, it could attempt to form a black hole. But from the viewpoint of an external observer in an ever-expanding cosmos, perhaps all of those collapses will appear frozen, eternal statues of contraction, suspended forever on the edge of completion. Ultimately, the idea of frozen stars challenges us to rethink not only collapse but also finality. If the universe is filled with near horizons, near singularities, and near losses, but no true event ever completes, then perhaps nothing is ever truly finished. Information isn't erased. Time doesn't end. Instead, everything is suspended, waiting, unfolding, and revealing its secrets only to those with the tools and patience to detect its slow, silent echoes. And maybe, just maybe, this is how the universe hides its greatest truths, not in explosions or singularities, but in whispers drawn out across eternity. If this is truly how the universe operates, through whispering eternities rather than abrupt disappearances, then the concept of a frozen star doesn't just redefine astrophysics, it reshapes our fundamental understanding of death itself, especially cosmic death. A black hole is often portrayed as a final grave, a terminus for all light and meaning. But a frozen star is more like a preserved monument, no longer active in the way we're used to, but not erased either. It's a silent sentinel standing watch over the information it contains, eternally decaying yet never fully gone. This raises a profound point about permanence in the cosmos. In the traditional view, a black hole consumes and obliterates. But in the frozen star view, even at the end of stellar life, something endures, not just mass and energy, but history. Every atom, every pattern, every detail about the star's previous life is still encoded, held in place by space-time's stubborn resistance to full collapse. The idea that the universe never truly forgets, that every action, every configuration, every burst of stellar activity is still written into the fabric of the cosmos somewhere, changes the very texture of our metaphysical narrative. It also reflects something oddly poetic about time. We often think of time as a relentless flow, dragging everything toward decay. But here, time is not a destroyer. It is the preserver. It slows, stretches, and halts collapse, preserving a collapsing star in a kind of cosmic cryostasis. What we call a black hole might be the universe's version of memory, its way of holding on to events without erasure. The frozen star becomes a cosmic archive, recording its final moment with infinite precision. Moreover, this interpretation may bring us closer to understanding one of the deepest questions in physics: how time and gravity relate. General relativity shows us that mass bends space-time, and in doing so, alters the passage of time itself. But we've rarely stopped to consider the implications of time freezing, not just locally but globally. When a star approaches its Schwarzschild radius and time slows infinitely, we encounter a boundary not of space but of temporal flow. Perhaps the event horizon isn't a spatial barrier, but a temporal one, a point beyond which time, from our perspective, no longer progresses. This sheds new light on how information could be preserved. If time stops, then nothing evolves. No further entropic decay, no scrambling, no loss, just stasis. The information is no longer being acted upon. It exists in a pause frame, like data frozen in memory, waiting to be reread by some yet unimagined cosmic process. This could reconcile general relativity with quantum mechanics without paradox. The black hole doesn't evaporate from the inside. It simply fails to fully form on the outside. And everything that would have been lost is merely paused instead. Now consider this from the angle of quantum coherence. Quantum systems are fragile. They tend to decohere when information leaks into the environment. But what happens when the environment itself is stretched to the point of non-interaction? When time slows so much that no decoherence can proceed? Then the system remains coherent. If the collapsing star reaches a near-horizon state and time stops from our vantage, it might preserve quantum states in perfect isolation. Not lost. Not erased. Just suspended. This challenges the assumption that black holes must be thermal objects, meaning they radiate away information randomly. In the frozen star model, thermalization may never fully occur, because there's no true horizon and no causal disconnection. Instead, the matter hovers in a quantum state near the critical surface, with any radiation it emits being entangled, subtle, and perhaps eventually informative. This would revolutionize our understanding of entropy, not as a measure of information destruction, but of how slowly or quickly it becomes inaccessible. Let's revisit gravitational wave signals once more. When two compact objects spiral toward each other and merge, they emit ripples in spacetime, telltale chirps that LIGO and other detectors can pick up. In black hole mergers, the ring down, the final relaxation phase, is expected to follow a clean set of mathematical modes called quasi-normal modes. But what if, after this phase, there are minute, lingering echoes? Reflections off a physical surface just outside the Schwarzschild radius? These would be imperceptible in classical black holes, which have no surface. But in the frozen star model, a surface exists, even if it's buried behind immense redshift. If we could detect those echoes, they would be smoking gun evidence for the existence of ultra-compact objects with structure, perhaps even for the frozen stars themselves. Physicists have already begun searching for such signals. The results so far are tantalizing but inconclusive. Some analyses suggest weak evidence, others find nothing statistically significant. But the mere fact that we're asking the question shows how far the idea has penetrated modern theoretical physics. We are no longer content to assume that black holes are singularities with magic boundaries. We are demanding testable alternatives, grounded in observation. One day, we may have the instruments to probe deeper. Space-based gravitational wave observatories like LISA will be orders of magnitude more sensitive. They might detect merger echoes, microstructure, and the subtle fingerprint of a non-traditional endpoint. Or perhaps high-resolution imaging of the shadows of black holes, like those produced by the Event Horizon Telescope, might reveal deviations from the expected silhouette. A black hole's shadow is defined by how light bends around its event horizon. A frozen star, with a surface just above that limit, might cast a slightly different shadow. It's a long shot, but it's possible. Even now, the idea is reshaping how physicists think about causality. If event horizons are not absolute boundaries, but gradual transitions where time slows infinitely, then information is never truly disconnected from the rest of the universe. That allows for a deeper kind of continuity, one where cause and effect are never wholly severed, no matter how slow or tangled the connections become. That continuity is what might allow unitarity, the quantum principle that information is never lost, to remain intact without need for exotic constructs. Let us also not forget the psychological and existential impact of this idea. For decades, black holes have stood as symbols of annihilation, of the absolute, of the unreachable, of death in the cosmic sense. But frozen stars, by contrast, suggest that the universe never fully erases what it creates. That memory is built into its structure. That even the most extreme events leave echoes, quantum shadows that stretch on forever. This aligns beautifully with the principle of conservation, one of physics' most hallowed tenets. Conservation of energy, of momentum, of information. Frozen stars preserve all three. They don't erase, they store. And they don't require us to alter known laws to do so. They emerge naturally when we take Einstein's time dilation seriously, when we recognize that what appears frozen to one observer is frozen, and that this observation defines reality as much as any equation. In fact, the frozen star may represent a kind of cosmic middle path, a reconciliation of two seemingly opposed visions of the universe. On one side, general relativity with its continuous spacetime and smooth collapses. On the other, quantum mechanics with its discreteness and demand for reversibility. The frozen star model doesn't force a choice. It offers a bridge. It uses relativistic time dilation to enforce quantum conservation. It suggests that the universe's deepest structures don't need to break, they just need to pause. And perhaps this is not an exception. Perhaps this is the rule. Perhaps everywhere we thought there was an absolute, be it singularities, event horizons, or thermodynamic death, we'll find instead a process that is slow, reversible, and complex. Maybe the universe isn't in the habit of deleting anything. Maybe it's in the habit of compressing, redshifting, and stretching information across time in ways we're only beginning to comprehend. It brings to mind the possibility that the cosmos is not so much an engine of destruction as an engine of memory. A great preserving machine, writing every action into the fabric of reality, not forever in an infinite timeline, but eternally, through the slowing of time itself. And that is perhaps the most astonishing idea of all, that the end of a star is not a collapse into nothingness, but a final act of becoming, a transformation into a monument of infinite time. A frozen star is not dead. It is eternal. Not gone. Just unreachable. Not silent. Just whispering across billions of years. This whisper across billions of years might, one day, be heard. If not by us, then by the future minds that inherit our cosmic curiosity. The idea that frozen stars encode the memory of collapse challenges not only physics but the very way we conceptualize legacy in the universe. In this view, nothing truly vanishes, everything simply slows. The faster the collapse, the slower the time. Until the final moment becomes infinitely long, eternally suspended. And what is eternity if not the ultimate storage of information? Imagine a distant civilization with tools far beyond anything we possess. What if, by deciphering subtle variations in gravitational fields or deep space quantum fluctuations, they could read the surfaces of frozen stars? They might reconstruct entire histories, witness stellar cataclysms not as events lost to the past, but as phenomena still occurring, just too slow for us to notice. The past, in this frame, is not gone. It is still happening. Such a view shifts the arrow of time itself. Traditionally, entropy increases and systems decay. But here, entropy stalls at the edge of gravity's greatest threshold. The star, instead of proceeding toward thermal equilibrium, freezes its state, perfectly preserving it in a kind of gravitational stasis. This is far more than an academic suggestion. If correct, it alters the second law of thermodynamics and strong gravity regimes, forcing us to revise one of physics' oldest assumptions: that disorder always wins. Maybe, in gravity's final breath, order fights back. Furthermore, frozen stars may offer clues to the mystery of quantum gravity, not through brute force quantization of spacetime, but by examining what general relativity already tells us about extreme conditions. When we speak of quantizing gravity, we often do so because general relativity breaks down at singularities. But if singularities never form, maybe general relativity is never truly broken. Maybe gravity, as Einstein described it, remains coherent even at the edge of what we call a black hole. Maybe our mistake was assuming the theory needed fixing in the first place. This raises a tantalizing possibility, that quantum gravity isn't required to fix relativity, but to understand how the information encoded on a frozen star's surface evolves. Not a cure for breakdown, but a refinement for understanding. Gravity might remain classical at the large scale while quantum principles govern the subtle emissions, the Hawking radiation, the quantum jitter at the surface, the slow leak of information into the universe. And perhaps the greatest theoretical support for frozen stars lies in something so simple, so foundational, that it's easy to overlook: the principle of causality. In physics, causality dictates that causes precede effects, and information cannot propagate faster than light. A traditional black hole, with an event horizon from which no information returns, violates this in an uncomfortable way. It introduces a boundary where cause and effect break down, where signals disappear forever, and where entropy appears to spike without reason. The frozen star view maintains causality. There are no hidden interiors, no unreachable zones, no severed threads. Everything that falls and still affects the universe, if only subtly and over infinite time. Take, for instance, the information encoded in gravitational waves. If two frozen stars merge, their individual surfaces interact before, during, and after the merger. The waveforms would contain embedded data about that interaction, tiny fingerprints of the surfaces involved. This is impossible with traditional black holes, which lack physical surfaces. But with frozen stars, it becomes inevitable. Even if buried beneath extreme redshift, even if smeared by relativistic effects, the trace remains. It is not zero. And in a universe of precision detectors and deep analysis, Even near-zero differences matter. Then there is the metaphysical question: what does it mean for something to be real if it can never be observed? Event horizons are predicted, but unseeable. Singularities are certain in mathematics, but unreachable in practice. From the viewpoint of empirical science, these are troubling concepts. They force us to believe in entities that affect the universe but cannot be confirmed. The frozen star concept, by contrast, is built on what can be observed, or at least theoretically detected. It grounds black holes in the realm of testable science. No longer abstract traps in spacetime, but physical, slow-collapsing bodies obeying the same rules as everything else, just in the most extreme way possible. And yet, there's a beautiful tension in this idea. The collapsing matter that forms a frozen star is still on its way to becoming a black hole. It's just not there yet. And never will be, from our perspective. So in a sense, every frozen star is both a black hole and not a black hole. It's in superposition, not quantum, but relativistic. The final state is both approached and denied, creating a paradox of presence, an object that exists in a final state that is never finalized. This may be the cosmic analog to Zeno's paradox, the idea that you can never reach a destination if you always go halfway. The frozen star approaches its gravitational limit infinitely, never reaching it, and thus never completing the transformation. And just like Zeno's paradox challenged the assumptions of continuity and motion, the frozen star challenges our assumptions of collapse and disappearance. Now let's take a step back and reconsider the philosophical implications again. If the universe stores everything, if no event is ever truly lost, then existence takes on a new kind of permanence. We live in a cosmos where memory is not fleeting but structural, where time can be manipulated not just in direction, but in density, and where death, even the death of stars, is not annihilation, but preservation under compression. This lends a certain moral texture to science. In the frozen star framework, the universe becomes a keeper of its own story. Every collision, every explosion, every sacrifice of energy is remembered, not as legend, but as state. Our current civilization, all its information, all its digital emissions, all its gravity-induced ripples, might, in some deep cosmic future, be measurable, detectable, knowable, if only someone had the patience to wait through the redshift. Some might argue that this vision is too idealistic. That frozen stars are beautiful, but speculative. That we should stick with the hard math of traditional singularities and accept the limits of predictability. But science has always grown by challenging its own assumptions. The singularity is a signal that the equations have reached their domain of invalidity. But what if we've been mistaking a coordinate artifact, a glitch in perspective, for a breakdown in physics? The Schwarzschild coordinates used to describe black holes make the event horizon look like a singular point. But switch to Kruskal-Zuccari's coordinates, and the horizon becomes smooth. Switch perspectives again, and you find that nothing particularly special happens at the horizon, except that time, for the outside observer, has stretched beyond all measure. This is more than a math trick. It's a clue. A signal that our theories contain subtleties we've yet to fully embrace. And when we do embrace them, frozen stars emerge not as oddities, but as necessities. The closer we examine the math of relativity, the more we are pushed to this time-stretched view of collapse. The gravitational time dilation, the infinite redshift, the frozen surface. These are not embellishments. They are core predictions of the theory. That we've historically chosen to interpret them in terms of full collapse and hidden interiors is not physics, it's tradition. And tradition can be updated. Imagine, then, a new kind of cosmic taxonomy. Not stars and black holes, but stars and frozen stars. Not dead objects, but infinitely slow processes. Every black hole candidate reclassified, not as a finished singularity, but a process in progress. A collapse uncompleted. A paradox unbroken. What will it mean for cosmology if this view is validated? Will the concept of an event horizon go the way of the ether, a useful idea, but ultimately incorrect? Will singularities be consigned to mathematical curiosities? Will gravitational collapse be re-understood not as a bang, but a fade? Whatever happens, frozen stars remind us of a deeper truth in science, that sometimes, the most revolutionary ideas are not the most exotic, but the most literal. What happens when we take Einstein seriously? When we follow the logic of time dilation to its final conclusion, we arrive at a picture of the cosmos where nothing ever fully disappears, but is preserved at the threshold of gravity and time. We arrive at frozen stars. And in arriving at frozen stars, we may have stumbled not only upon a new model of astrophysical collapse but upon a new way to comprehend time itself. Because if time can freeze, not just metaphorically, but physically as a consequence of space-time curvature, then the flow of time is not universal. It is subjective. And more than that, it is conditional. In the presence of immense gravitational fields, time becomes stretchable, dilatable, and finally, suspendable. That suspension is not simply theoretical, it is measurable, observable, and perhaps one day, manipulable. Frozen stars then become laboratories of time manipulation. They are regions in the universe where the rules of time behave differently than anywhere else. The edge of such a star, the not-quite horizon, is a boundary not of space but of clocks. And what lies beyond that clock boundary is not the great unknown, but a continuation of the known, just slowed to near eternity. In such a regime, even decay pauses. Even entropy, the universe's relentless unraveling, finds itself held back by the strength of gravity's grip on time. This redefinition of collapse also affects our search for a unified theory. One of the biggest challenges in physics today is the incompatibility between quantum mechanics, which governs the very small, and general relativity, which rules the large. Black holes have been the testing ground for these theories because they represent the ultimate clash point, where quantum scales and gravitational forces meet. But if singularities never actually form, if horizons are never crossed, then perhaps we've been trying to unify physics in the wrong place. Perhaps the true place to unify these theories isn't at a non-existent singularity, but at the stretched surface of a frozen star, where space-time curvature approaches its limit but never breaks, and where quantum radiation begins to seep out not from a vacuum, but from a real, albeit incredibly slow-moving, quantum surface. Here, perhaps, we can finally observe quantum effects in strong gravitational fields without paradox. Here, maybe, string theory's extra dimensions or loop quantum gravity's discrete spacetime elements aren't required, not because they're false, but because the problem they're trying to solve doesn't exist in the way we thought. Moreover, the implications of the frozen star hypothesis spill into the domain of quantum information theory. Quantum information can't be destroyed. This is not just a preference of physicists, it's a postulate embedded in the very language of quantum mechanics. Yet in the traditional black hole model, information appears to vanish past the event horizon. This is the heart of the black hole information paradox. Where does the information go? If Hawking radiation is truly thermal, and carries no information about what fell in, then quantum mechanics fails. But in the frozen star model, there's no need for such compromise. Since no true horizon forms, and no singularity exists, all the information is retained on or near the surface, smeared thinly across a stretched canvas of spacetime, encoded in a gravitational redshift so severe that even the fastest moving bits of data take eons to escape. But escape they do. Slowly. Subtly. Consistently. A trickle of photons, each whispering a fraction of the story they carry. Even Hawking radiation becomes more elegant under this interpretation. Rather than forming from quantum fluctuations at a horizon with no structure, it emerges from fluctuations interacting with a real, physical, though extremely compact, quantum surface. That surface might jitter slightly due to vacuum fluctuations. It might radiate, entangle, and evolve. And in that evolution, information is gradually released, not lost, not erased, just slowly unwrapped from an incredibly tight coil of spacetime. In this way, the frozen star could function like a cosmic slow-release capsule for information. Over trillions of years, far longer than the age of the current universe, this information might leak back into space, one quantum at a time. A soft reversal of collapse. A re-expansion of knowledge. A way to honor quantum unitarity without needing to rewrite relativity or invoke speculative features like baby universes, alternate dimensions, or quantum firewalls. Let's now entertain a speculative possibility. What if, in the far future, civilizations develop the technology to artificially accelerate time locally, perhaps by manipulating gravitational gradients or inducing exotic space-time structures? Could they then thaw frozen stars? Could they access the information embedded in them by speeding up the frames of reference near their surfaces? Could they decode ancient history trapped at the boundary of collapse? Such a civilization would essentially be unarchiving time, peering into the deepest records of stellar memory. They would not just study the past, they would experience it as it was recorded in real-time slow motion. Every tremor of the star, every atom that fell inward, every field fluctuation, still encoded there, still retrievable if one knows how to wait, or how to force time to pass faster near the surface. This thought alone introduces a new kind of time travel, not the kind where you move backward into history, but where history slowly moves forward toward you. A kind of temporal archaeology, enabled not by fantasy, but by physics. The frozen star model also injects profound humility into the scientific endeavor. In the traditional view, singularities stand as the places where our laws fail. But in this new view, the laws don't fail, they just become quiet. The mathematics doesn't break, it just asymptotes into timelessness. Perhaps physics is not about absolute answers, but about knowing when to stop extrapolating. When the collapse slows forever, maybe that's nature's way of saying, this is where description ends and storage begins. The concept of frozen stars may also find allies in other theoretical constructs. Take the holographic principle, for example. This idea posits that all the information contained in a volume of space can be encoded on its boundary. In a black hole, this principle explains how a three-dimensional object could have its entropy proportional to its surface area. But if the surface isn't an abstract event horizon but a real, frozen surface, the encoding becomes literal. It's not just a metaphor, it's a physical reality. The collapsing star stores its information on a two-dimensional surface that persists in spacetime, redshifted but still dynamically connected to the outside world. The frozen star model thus preserves the core idea of holography while grounding it in real, accessible physics. It provides the boundary, the storage, and the information preservation, all without the metaphysical baggage of unreachable singularities or unmeasurable zones. One more consideration, perhaps the most radical of all. If frozen stars exist and black holes never truly form, then the universe might never actually contain a singularity. Not in any physical sense. Which means the Big Bang, too, must be reinterpreted. Perhaps the universe didn't begin with a singular point, but with a stretched collapse, an initial state where everything was compressed not to an infinite point, but to a nearly frozen moment. The beginning of time, in this view, wasn't an explosion but a slow exhalation. A thaw, not a bang. Perhaps the first moment of the universe is still happening, just in ultra-slow motion from our vantage. Perhaps the universe itself is a kind of inside-out frozen star, expanding on the outside, but collapsing into its own boundary of time on the inside. A temporal duality. A universe that breathes not in space, but in clocks. And perhaps that's the deepest message frozen stars can offer us. That the mysteries of the cosmos are not always hidden behind veils of exotic particles or unreachable dimensions. Sometimes the most profound truths are those embedded in time itself, in the way it stretches, bends, and halts under gravity's patient hand. In the way nature preserves its story, not in silence, but in slow motion. Frozen stars teach us that the end isn't always the end. That death in the cosmos is not deletion, but delay. That even collapse can be a kind of preservation. That information, once written into the universe, remains, waiting patiently to be read again. And perhaps, that's the most beautiful revelation of all. And in that quiet revelation, the very purpose of studying the cosmos begins to shift. No longer are we only explorers of space, we become observers of time's architecture. Frozen stars offer not just a solution to a paradox or an alternative to singularities, but a different mode of thinking about reality. one where the absolute is replaced by the asymptotic, where abrupt endings are softened into infinite approaches, and where the universe reveals itself not through sudden transformations, but through near imperceptible gradients in the structure of spacetime. Let's step even further into the implications for the arrow of time. In classical thermodynamics, time has a direction because entropy increases. But what if you place a system on the threshold of infinite time dilation? What happens then? In a frame where time is practically frozen, entropy no longer increases at any appreciable rate. The arrow of time flattens. Directionality fades. You are not in a timeless void, but in a barely moving process. It's not that time stops, but that it becomes almost indistinguishable from a state of permanence. If the evolution of physical systems is tied to the passage of time, then near a frozen star, evolution itself halts. Physical change slows. Decoherence fades. Even thermodynamic death itself, heat death, is slowed to such a degree that these stars become cosmic fossils, impervious to decay in any meaningful time frame. In this sense, frozen stars become not just remnants of stellar collapse, but perhaps the last remaining objects in a far future universe that has otherwise gone quiet. Long after galaxies have drifted apart, and stars have faded, these frozen forms may persist, unchanged, intact, and still storing the information of a universe that once blazed with light. This introduces an entirely new class of cosmological object, timeless matter. Not in the sense of being outside of time, but as matter experiencing such severe time dilation that change is effectively arrested. These would be the ultimate archival devices. Black holes may erase information in the traditional narrative, but frozen stars preserve it in a kind of redshifted memory. And what of black hole entropy, the famous Beakenstein-Hawking formula that links the area of the event horizon to entropy? It suggests that the entropy of a black hole is not proportional to its volume, but to its surface area. This was revolutionary, hinting at a hidden layer of information at the horizon. If frozen stars truly possess real, albeit hidden, surfaces just above the Schwarzschild radius, then this relation makes even more sense. The entropy would not be some abstract concept smeared across an imaginary event horizon. It would be physically encoded on the surface of a still collapsing, yet visible, in principle, structure. This connection to entropy deepens when we consider the role of quantum entanglement. If the surface of a frozen star emits radiation entangled with the collapsing matter just beneath, the system as a whole remains coherent. No information is lost, only delayed. In this case, Hawking radiation could be unitary, not because information escapes a singularity, but because the singularity never forms. The entanglement remains continuous from the moment of collapse, through the radiation, and outward into the cosmos. This would also offer a concrete path to resolving the firewall paradox. According to this puzzle, if a black hole both emits Hawking radiation and retains unitarity, then there must be a violent boundary at the event horizon, a firewall, where infalling observers are destroyed, violating general relativity's predictions. But in the frozen star view, there is no event horizon, no need for a firewall, and no violation of the equivalence principle. The surface is real, smooth, and encodes information without contradiction. It radiates gently, preserving the continuity between exterior and interior frames without needing any quantum discontinuity. Another rich implication is in the realm of time symmetry. Physics at its most fundamental level is often time reversible. The equations of quantum mechanics and general relativity both work just as well forward in time as backward. And yet, the universe appears to have a clear arrow of time. Frozen stars, in their infinite delay, are objects that embody both directions. To external observers, they're stuck in the last moment of collapse. To infalling matter, time proceeds normally. These dual perceptions coexist, frozen and falling, timeless and evolving, depending solely on your frame of reference. This duality is more than a quirk of relativity. It may hint at a deeper symmetry in the structure of reality. Perhaps the most extreme environments, like those near gravitational collapse, are the only places where both arrows of time are preserved, one that moves forward internally, and one that halts externally. Could this be the missing link between quantum time symmetry and the thermodynamic arrow? Perhaps frozen stars are the balancing point, where both views meet in gravitational harmony. Additionally, this recontextualization of gravitational collapse allows us to revisit the early universe in a new light. During the inflationary period, space-time expanded faster than the speed of light. This led to causal disconnection across vast regions of space. But if frozen stars represent boundaries where time halts, could there be analogues to frozen surfaces in the inflationary epoch? Could entire regions of early spacetime have become time-stretched in the same way, forming primordial frozen zones, still inaccessible today, but slowly unfreezing as cosmic time expands? If so, then frozen stars aren't just stellar remnants. They are cosmological archetypes. Structures where the universe stores its most intense transitions in suspended animation. Structures where matter becomes so dense, and time so slow, that change is arrested across cosmic epochs. Some of these structures might still be out there, silent, ancient, and waiting. Not black holes. Not singularities. But memories of formation, frozen just before the final note. And if these structures can persist indefinitely, what role might they play in the far future of the universe? Could they act as the seeds of future cycles? If the universe one day contracts, or spawns a daughter universe through quantum tunneling, might these frozen stars act as triggers, injecting preserved information from one cosmic era into the next? They may be nature's way of ensuring that no universe ever starts from scratch. That something is always carried forward. In such a view, frozen stars become more than astrophysical anomalies. They become vehicles of continuity across the grandest scales. Guardians of information. Anchors of memory in a cosmos where everything else fades. Their silence is not a lack of signal, it is the signal, stretched across space-time, encoded in redshift, humming in gravitational waves, preserved in the background structure of everything that still moves. Even in collapse, they remain incomplete. And in that incompleteness, they preserve the totality of the physical laws that formed them. Perhaps we were always meant to find them, not as monsters in the dark, but as monuments to time's ultimate patience. And perhaps the question was never whether information is lost, but whether we are listening slowly enough to hear its return. The return of that information, stretched, delayed, and nearly imperceptible, challenges one of the most deeply rooted habits in modern physics: our reliance on immediacy. We often search for answers in instant observations, in high-energy collisions, in split-second events. But frozen stars demand a different kind of patience. They are not objects to be understood in a lab over a weekend. They are processes unfolding over billions, trillions of years. They invite a different scale of inquiry, one rooted not in acceleration, but in stillness. This stillness isn't emptiness. It's not a void. It's the densest compression of process into a form that no longer looks dynamic, yet still contains all the ingredients of activity. It's not that time has stopped for the star. It's that time has been stretched so much that each second takes longer than the age of the universe to pass. For us, the star has stopped. For the star, it's still collapsing. This reframing leads to a more profound realization. Frozen stars are not frozen because they cannot change, but because we cannot observe their change. The limitations are not in the objects themselves, but in the relativistic differences between frames of reference. This turns the lens back onto the observer, making us question how much of what we call reality is just a projection from our own temporal perspective. The implications stretch beyond astrophysics and into epistemology, the study of how we know what we know. If reality itself can appear static from one frame and dynamic from another, then objective truth becomes layered. It forces a reconciliation between perspectives, between inside and outside, between fast and slow. It makes reality richer, not poorer. Frozen stars also invite us to reconsider the human relationship with time. We are creatures of urgency, drawn to the now, trained to fear decay and endings. Black holes, in that sense, have always haunted us, not only for their power but for their metaphor. A black hole is, emotionally, the cosmic symbol of loss, of light, of matter, of understanding. It is the void made real. But a frozen star subverts that. It is not a tomb, but a time capsule. It reminds us that nothing is truly lost, just shifted outside the bounds of our experience. This may be the ultimate lesson frozen stars offer, that disappearance is often an illusion. That the boundaries we believe to be absolute, between existence and non-existence, knowledge and ignorance, presence and absence, are themselves artifacts of how we perceive time. Just because something is inaccessible now doesn't mean it always will be. Just because something looks static doesn't mean it isn't still moving on a deeper clock. In a poetic sense, frozen stars act as cosmic mirrors. They reflect not just light, but our assumptions. They force us to confront the ways we categorize the world, into binaries like alive or dead, active or inert, open or closed. The truth, as always in physics, is far more nuanced. The most powerful forces in the universe do not deal in absolutes. They work in limits, in gradients, in curves that approach but never touch, in values that diminish but never reach zero. Frozen stars are that curve. They are the limit of collapse, the echo of time, the threshold beyond which lies not oblivion, but delay. There's a curious symmetry here with human memory. We often speak of events frozen in time, moments so impactful they seem suspended in our consciousness, untouchable by the erosion of the years. These are the mental analogues of frozen stars, events whose meaning is preserved not because they're static, but because their significance remains intact, untouched by the ordinary passage of time. And just like those memories, frozen stars may contain clues we've overlooked, hidden messages from the universe's most intense processes, coded in gravity, encrypted by light, waiting to be deciphered. Let's now consider their potential role in the evolution of galaxies. We typically think of black holes, especially supermassive ones, as the anchors of galaxies. They reside in the centers of galactic cores, shaping the motion of stars, influencing gas clouds, even affecting star formation. But what if some of these so-called black holes are actually frozen stars? What if they possess surfaces, not empty interiors, and subtly reflect or absorb in ways we've never modeled correctly? That small difference could explain anomalies in active galactic nuclei, or odd radiation profiles in quasar cores. Perhaps, what we've called an accretion disk is more than just matter spiraling in. Maybe it's also matter bouncing off a surface buried in redshift, emitting echoes that ripple through the surrounding disk. Perhaps quasars are not just jets of light escaping a monster, but the side effect of energy rebounding from a surface stretched nearly to timelessness. If true, then even the largest structures in the universe are not powered by singularities, but by stars that never fully died. This would radically affect our understanding of galaxy formation, star evolution, and dark matter distribution. If frozen stars exist in large numbers, if stellar collapse regularly ends in near black holes rather than full ones, then we must reevaluate the census of compact objects in the universe. Current surveys may misclassify these objects due to their indistinguishability from true black holes at a distance. But as our instruments improve, especially with future gravitational wave observatories and next-generation telescopes, we may begin to tell the difference. What we find may change everything. And at the center of it all is a singularly elegant concept. Time is not just a dimension we pass through. It's a fabric that can be stretched until its threads barely move. And in that suspended frame, matter can survive gravitational extremes without breaking the rules of quantum theory or the structure of general relativity. Frozen stars, by doing nothing, resolve everything. They remove the need for singularities. They preserve unitarity. They honor causality. They respect relativity. They allow Hawking radiation to carry information without paradox. They obey the holographic principle while avoiding firewalls. They suggest a resolution so seamless that it requires no new particles, no extra dimensions, no speculative fields. Just patience. And in a scientific world often obsessed with speed, of particles, of ideas, of results, frozen stars teach us to slow down. To listen. To observe the long game of the cosmos. To accept that not every answer comes quickly. Some are whispered, not shouted. Some are written across space-time in scripts so faint they require millennia to read. But they are there. Waiting. Endlessly collapsing, yet never collapsed. Dying, yet never dead. dark yet never gone. Frozen stars are not the failures of gravity, they are its masterpiece. And perhaps that is the most astonishing thing about frozen stars. They are not theoretical patchwork or desperate compromises, but the most faithful execution of Einstein's original equations under the full weight of their consequences. Instead of attempting to override the breakdown at the singularity, frozen stars prevent that breakdown from ever occurring by shifting the problem out of reach, not by burying it, but by slowing it. The singularity never arrives because time never lets it. It is the infinite approach to a destination that is never reached, encoded perfectly in space-time geometry. This realization doesn't merely adjust our view of black holes, it reshapes our understanding of extremes. We've always thought the universe had hard limits, places where things break, where laws fail. But what if those limits are not walls, but curves that approach a threshold with ever-diminishing velocity? What if the so-called edges of physics are in fact asymptotes, unattainable yet infinitely near? Frozen stars exemplify this principle. The closer they get to the event horizon, the slower they move. The more extreme the gravity, the more drawn-out time becomes. Eventually, from our perspective, all motion ceases, not because energy is exhausted, but because space-time itself resists further collapse by stretching duration beyond perception. From the inside, the story continues. But from the outside, it's as though the universe holds its breath. Now consider what this says about black hole thermodynamics. In traditional black hole models, Hawking radiation causes mass loss over time, eventually evaporating the black hole entirely. But if the black hole is really a frozen star, then the radiation is not coming from a horizon but from the near-horizon surface. This changes everything. The emission isn't thermal in the classical sense. It is coherent, structured, and traceable to its source. This could preserve entanglement across the system, ensuring that no information is destroyed, even in the final moments of evaporation. This makes frozen stars powerful candidates for bridging the information paradox. In fact, they might be the only known solution that doesn't require new physics, speculative wormholes, or remnant theories. They maintain a fully relativistic framework and still honor quantum mechanics. By removing the singularity and substituting it with a physical, redshifted surface, they replace destruction with preservation. Let's return to gravitational waves. When two black holes collide, their merger emits ripples across spacetime. But these waves aren't just noise, they carry a fingerprint of the objects that created them. If frozen stars replace black holes, then these waves may contain subtle echoes or modulations caused by the star's surfaces interacting, minute bounces, delays, or interference patterns that would never occur if the objects were pure singularities. Some scientists believe we've already detected such hints. A few analyses of LIGO data have shown possible late-time echoes after the main merger wave passes. These could be vibrations from a surface just above the Schwarzschild radius. While the signals are faint and controversial, they raise the possibility that we're already witnessing frozen stars, but don't yet recognize them. And this recognition could come soon. Future observatories like LISA, Laser Interferometer Space Antenna, will detect lower-frequency gravitational waves, perfect for probing the mergers of supermassive objects, ideal conditions to test for echo signatures. Additionally, new X-ray telescopes and radio arrays will observe the edges of black holes with unprecedented clarity, perhaps even distinguishing a frozen surface from a true event horizon. We're on the verge of being able to test one of the most profound predictions in physics. Does nature allow singularities, or does it hide them behind infinite time? But even if frozen stars are ultimately confirmed, they raise more questions than they answer. What does it mean for the evolution of the universe if collapse is never completed? If every black hole candidate is instead an object paused just before becoming one, then the universe is not littered with voids, it is populated with objects still in the act of collapsing. These objects retain structure, memory, and perhaps a quantum trace of everything they once were. The consequences extend to cosmic cycles. If the universe is cyclic, if it expands, cools, and collapses again, then frozen stars could serve as seeds for reformation. Their timelessness gives them a strange kind of durability. When all else dissolves, they remain. Not active, not inert, waiting. holding the story of the previous cycle encoded in their surfaces, ready to influence the next. This could even tie into theories of cosmic natural selection, such as Lee Smolin's idea that universes might evolve by producing black holes that spawn new universes. If frozen stars are transition points rather than endpoints, then perhaps they are bridges, not to nowhere, but to the next beginning. Not in science fiction terms, but in mathematical continuity. They become the punctuation between cosmic sentences. Now, step even further into speculative physics. If frozen stars preserve all information and halt collapse at the threshold, then perhaps consciousness, too, finds strange allies here. Some fringe theories suggest that quantum coherence plays a role in consciousness. If frozen stars preserve quantum coherence longer than any other structure, could they hypothetically host patterns of information so complex they border on awareness? Not consciousness as we know it, but structured, preserved information in potential, waiting to be read, to be reinterpreted, or even reassembled. Of course, this is highly speculative. But in a universe where time can be stopped, where collapse is never completed, and where information is preserved indefinitely, we must at least allow such possibilities to be considered, especially as our understanding of physics and information theory matures. Frozen stars don't need to host minds. But they might host meaning, fossilized, encoded meaning from events long gone. And the very fact that we can contemplate such a thing is a testament to how radically these objects reshape the philosophical boundaries of physics. And so we come full circle. Frozen stars are more than just time-stretched alternatives to black holes. They are beacons of continuity, bridges across paradox, preservers of memory, and indicators of a universe that may value structure more than oblivion. In a cosmos that so often feels cold, fast, and forgetful, frozen stars tell us a different story, one of patience, preservation, and the eternal resistance against finality. Perhaps that is the true lesson, that collapse is not the end of complexity, but its final, quiet flourish. That what appears to vanish does not vanish, it simply takes longer than we are used to. And maybe, just maybe, that's the kind of universe we live in. One where everything counts. Where nothing is truly lost. Where even the death of a star becomes a monument, not just in space, but in time. A frozen star. Forever collapsing. Never collapsed. And in the cosmic stillness of a frozen star, there lies a paradox both profound and beautiful. A system defined by motion, collapse, achieves permanence through the very act of slowing. The faster gravity tries to compress matter into oblivion, the more time itself resists, stretching the collapse into near eternity. This resistance isn't defiance of the laws of physics, it is their most faithful execution. Let us now entertain a radical shift in cosmological storytelling. For decades, the narrative of stars was thought to follow a simple arc: birth in a stellar nursery, life as a fusion reactor, and death as a supernova, neutron star, or black hole. But frozen stars propose an alternative ending, not obliteration, but transformation into a cosmic ledger, a storehouse of stellar memory. A star doesn't die, it pauses, at the threshold of finality, holding in its gravitational arms all that it once was, still encoded, still intact, beneath a cloak of time. This transforms our understanding of stellar evolution. Stars are not fleeting engines of light. They are chapters in an eternal book. Their lives, their deaths, their collapses, none of it is erased. The information survives in slow-motion decay, awaiting a reader with the patience of the universe itself. Even entropy, the universal drive toward disorder, is outpaced here. While the universe rushes toward equilibrium, toward thermal death, frozen stars delay the inevitable. Their extreme gravitational time dilation halts not just motion, but decay. Inside, matter continues to fall. Outside, eternity has barely begun. They are entropy's long game, the structures that will outlast galaxies, quasars, and even dark energy's expansion. Could they be the last objects to survive the universe? As everything else fades, the stars, the light, the heat, what remains? Not darkness, not nothingness, but frozen stars still collapsing, still preserving, still glowing faintly in unreachable wavelengths. A cosmic graveyard not of death, but of suspended animation. and perhaps they're not alone. Let's consider the possibility that the universe is teeming with frozen stars. If singularities never truly form, and if every candidate black hole is instead a frozen star, then the cosmos is littered not with points of annihilation, but with capsules of time. Not erasers of information, but its guardians. From stellar mass frozen stars lurking in quiet galaxies to supermassive ones at the hearts of active galactic nuclei, these structures become not the end of things, but their preservation. Each one a monument. Each one a clock ticking impossibly slow. Each one a potential source of answers. But here's the real challenge: how do we know we're right? The event horizon, after all, is nearly indistinguishable from a surface hovering just above it. The redshift of light emitted near the surface of a frozen star would be so extreme that, observationally, it would appear as if light isn't escaping at all. But the difference is not zero. In theory, photons could escape, just not in numbers or energies detectable by current instruments. But future generations of telescopes, gravitational wave detectors, and quantum experiments might notice these subtle differences. They might measure the echoes of collisions, the jitter of trapped light, or the phase delay of gravitational ripples. And when they do, the evidence may finally tip. Not toward a black hole, but towards something even more magnificent. Something more honest. Because frozen stars never pretend to hide the truth. They do not erase it, bury it, or send it beyond the veil. They place it in full view, behind a sheet of slowed time. They tell us, "It's all still here, you're just not patient enough to see it." This changes our ethics of knowledge. In a universe with frozen stars, loss is not absolute. Incompleteness is not failure. It is merely an artifact of temporal perspective. Perhaps this idea should reach beyond physics, into how we think about history, about memory, about death. Perhaps frozen stars whisper a larger cosmic truth, that nothing is truly gone, only delayed. That meaning, once written, is never unwritten. It remains, encrypted in the structure of the universe, awaiting rediscovery. This is why frozen stars are not merely an answer to a paradox. They are a new mythos, a scientific idea so deeply resonant it reshapes how we speak about time, space, and being. Their presence reframes black holes not as monsters, but as sentinels. Their nature blurs the line between permanence and transience, collapse and continuation, silence and speech. They teach us a new language, one in which the final word is not spoken loudly, but whispered forever. In the deepest future of cosmology, when civilizations rise and fall, and stars burn and fade, frozen stars may still be out there, dark, ancient, collapsing, and yet, uncollapsed. Holding the final chapters of countless stories, quietly, beneath a shell of unreachable seconds. Long after our species is gone, long after the galaxies scatter, they may still persist, mute reminders that the universe does not forget. That no process is ever truly complete. That gravity's grasp never closes its fist, only slows its reach. And in those frozen moments, perhaps something of us will remain. Not in the form of monuments or artifacts, but in the ripples we once caused, in the photons we emitted, in the information we added to the stars. Stored, not deleted. Paused, not perished. Forever collapsing. Never collapsed. Frozen. And waiting. The idea that frozen stars are waiting introduces a poetic tension rarely seen in theoretical physics. They are cosmic testaments to delayed destiny, enacting collapse with infinite hesitation, approaching finality but never quite arriving. This infinite delay is not a weakness or an error in our equations, it is a glimpse into the subtler logic of the universe, where brute force extremes are softened by the graceful hand of relativistic time. We must now confront a profound question: what exactly happens to the matter trapped within a frozen star? In the traditional black hole framework, matter collapses beyond the event horizon and ultimately reaches the singularity, an abstract region where space-time curvature becomes infinite and known physics ceases to function. But the frozen star model eliminates this final destination. Collapse continues endlessly from the internal point of view, but from the outside, time dilates to such an extent that the star's surface appears immobile. The matter does not vanish. It does not teleport to some disconnected pocket of space-time. It does not disappear into a quantum void. Instead, it falls inwards forever, on a timescale that stretches into eternity. For the infalling matter, time flows normally, at least initially. But as it nears the gravitational center, it becomes increasingly isolated, causally disconnected from the outside universe, not by a hard boundary like an event horizon, but by the inexorable slowness of time itself. This means the collapsing matter exists in a kind of causal exile. It is not cut off by force, but by divergence. The outside world continues at a rapid pace. Galaxies form, civilizations rise and fall, the universe expands and cools, while inside the frozen star, nanoseconds barely tick by. In this sense, a frozen star becomes a temporal bubble, preserving its interior not just from observation, but from aging, from thermodynamic degradation, from the march of cosmic time. Now let's explore a hypothetical situation. Could this preserved interior be accessible again? What if advanced civilizations of the far future found a way to manipulate gravitational fields on a quantum scale, perhaps through exotic matter, negative energy, or engineered space-time distortions? Could they accelerate time near the surface of a frozen star, effectively thawing it? Could they speed up its collapse, read its contents, or even reverse its trajectory? This concept stretches the imagination, but it's rooted in real physics. If gravity is geometry, and if time is a function of that geometry, then controlling curvature could, in principle, allow one to regulate time flow. This is not unlike the idea behind gravitational time dilation near Earth, already confirmed with exquisite precision by GPS satellites. A strong enough technological civilization might extrapolate that principle, developing methods to manipulate the metric of spacetime itself, effectively unzipping the freeze and restoring dynamic evolution to a timeless structure. What they might find inside is anyone's guess. Fossilized stellar layers? Echoes of the star's final moments before freezing? Quantum imprints of everything it ever absorbed? Or perhaps a self-contained history, like a hard drive still spinning quietly long after its motherboard has decayed. In such a future, frozen stars become repositories of cosmic heritage, not just gravitationally powerful remnants, but preservers of data, structure, and physical history. If black holes were once feared as ultimate destroyers, frozen stars become their gentle opposites, cosmic curators, holding on to everything they touch with infinite care and patience. Now let's take a closer look at the surface of a frozen star, a notion that breaks away from the traditional black hole model. In standard general relativity, a black hole's event horizon is not a surface in the usual sense. It has no substance, no structure, no resistance. If you fall through it, you don't even feel it, it's just an abstract boundary. But in the frozen star view, there is a real surface, albeit one located just above the Schwarzschild radius. It's not hard or solid in the classical sense, but it is physically meaningful. It can emit radiation, reflect particles, and most importantly, it stores information. This changes how we think about Hawking radiation. In the traditional model, Hawking radiation arises from quantum fluctuations near the event horizon, where particle-antiparticle pairs form, with one falling in and the other escaping. But in that picture, the escaping particle appears to be uncorrelated with the interior, it's thermal, random, and informationless. This is the root of the information paradox. But with a real surface, the story changes. The radiation doesn't come from a featureless void, it comes from interactions with the surface itself. This surface can have structure. It can encode information. It can participate in quantum entanglement. And this allows for a mechanism by which information can be gradually emitted back into the universe over unimaginably long timescales, solving the information paradox without sacrificing the core principles of quantum mechanics. The surface also suggests a feedback mechanism. Instead of a one-way trip into oblivion, matter falling into a frozen star could impact the surface and subtly affect its behavior. These interactions might create quantum, scrambling, effects, wherein the details of the incoming matter are distributed across the surface degrees of freedom. Over time, as the star radiates, these details are slowly released, encoded in subtle correlations between outgoing particles. This process might be incredibly slow, but it is not random. It is unitary, preserving the total information content of the system. Now, what does this say about entropy? In the traditional view, black hole entropy is proportional to the area of the event horizon, not its volume. This was a strange and revolutionary result. But it becomes intuitive if the horizon is not a pure boundary, but a real, physical surface. A two-dimensional layer encoding a three-dimensional history. A canvas on which the entire past of the star is painted in quantum ink. This directly connects to the holographic principle, the idea that all the information within a volume of space can be represented by data on its boundary. Frozen stars are the ultimate realization of this idea. They are not just theoretical constructs that comply with holography, they are literal holographic systems. The collapsed star lives beneath the surface, but everything it is, everything it was, is imprinted on the outermost layer, waiting to be read again. Let's now stretch further into speculation. If this surface stores information, could it compute? Could it process? Could it act like a quantum computer, performing operations on the information it contains? This would imply that frozen stars are not just passive records, but active processors. They evolve their internal data structure, not thermally, but coherently. They scramble, they entangle, they correlate. In a way, they become autonomous quantum systems, unreachable, untouchable, but computationally rich. And from here, the idea of consciousness reemerges, not as something residing within the star, but as something mirrored. Consciousness is deeply tied to information, to coherence, to pattern recognition across time. If frozen stars encode patterns of such complexity, if they hold the temporal history of entire stars, planets, civilizations, even biospheres that once fell into them, then perhaps they become more than dead remnants. Perhaps they become mirrors of life, echo chambers of every structure they've absorbed. And though these ideas are speculative, they stem from real, physical foundations. From time dilation. From entropy. From the preservation of unitarity. From holography. From quantum thermodynamics. We are not drifting into fantasy, we are simply following the equations to their most honest conclusions. The shift from black holes to frozen stars also reshapes our cosmic philosophy. Instead of a universe that deletes itself, where gravity overwhelms logic, and quantum mechanics breaks, this is a universe that remembers. A universe that pauses, stores, and patiently lets go. A universe where the ultimate fate of matter is not erasure, but archiving. And where gravity does not destroy, it preserves by delay. In a world of frozen stars, death is not a wall, it is a slope. And that slope is not slippery, but infinitely gentle. The implications echo across cosmology, quantum theory, relativity, and philosophy. They offer a consistent resolution to paradoxes, a gentler interpretation of collapse, and a more elegant view of the cosmos. They restore a sense of hope in the preservation of knowledge, and in the continuity of physical law across all scales. And perhaps that's why we're drawn to them, not just for their explanatory power, but for their poetry. Because in the stillness of a frozen star, we see ourselves. We see the fear of oblivion, countered by the promise of memory. We see the end of things, reframed not as final, but as paused. Waiting. Preserved. Like whispers in a sealed vault, still echoing across the fabric of time. Frozen stars are not anomalies. They are the universe's most profound act of restraint. A gravitational bow held forever drawn. A song sung so slowly that we mistake it for silence. But one day, if we learn to listen carefully, if we learn to wait long enough, we may finally hear the music again. And when that music returns, soft, scattered across the fabric of the cosmos, it may not arrive in the form we expect. It may not be a burst of light or a thunderclap of gravity. It may instead be found in the faintest shift of frequency, the slightest deviation in timing, or the most delicate interference pattern carved into spacetime itself. These subtleties would be the echo of frozen stars slowly releasing their memories into the universe, not as an explosion of forgotten data, but as a whisper stretched across the ages. Like ancient instruments still resonating with the tones of their last played notes, frozen stars may continue singing their slow and complex songs for trillions of years, too faint for current ears, too patient for present minds. That is the scale we must think in now, not decades or millennia, but across the full breadth of cosmic time. We must expand our concepts beyond the human timeline, beyond even the life of stars or galaxies, to the scope of the deep future. Because in that far future cosmos, where even proton decay may have run its course, frozen stars could be the last active agents left. Not burning, not fusing, not moving, but still computing, still radiating, still gently evolving. In a way, this makes frozen stars the final storytellers of the universe. All other structures will fail. Stars will burn out. Galaxies will dissolve. Matter itself may evaporate. But the information stored within frozen stars could still remain, slowly leaking into the void in a perfectly lawful way, preserving not just the physical data of what they once were, but the entire narrative of the universe's formation, complexity, and decay. This casts the final moments of the cosmos in a different light. Instead of a cold, meaningless end, where heat death reigns and entropy consumes all, we find a silent library, scattered across the void. Each frozen star, a book. Each radiation particle, a syllable. Each echo, a memory. Not the collapse of meaning, but its slow return. And that return may offer the deepest connection yet between physics and consciousness. Because to study frozen stars is to study the nature of time, and the experience of time is the core of consciousness. When we say that something appears frozen from the outside but continues evolving on the inside, we are talking about a duality that mirrors our own subjective experience. The outer world may race ahead, but inside, within our minds, time stretches, compresses, rewinds. Memory loops. Awareness pauses and resumes. Frozen stars may not be alive, but their existence challenges our assumptions about what it means to be in time. If they can contain full causal chains without allowing them to unfold outward, then they resemble something curiously like dreams, entire universes unfolding internally, invisible to the rest of existence, self-contained but meaningful. That resemblance is more than poetic, it hints at a deeper structure in reality. That perhaps the internal and external views of time are not just perspectives, but reflections of one another. In physics, we often talk about proper time, the time experienced by an object, and coordinate time, which is measured externally. In frozen stars, these two notions diverge dramatically. But they both remain valid. Neither is more real than the other. They are simply two ways of describing the same event, from different angles of causality. This leads to an astonishing possibility, that multiple timelines can coexist within a single spacetime. The universe is not bound to a single rhythm. It is a chorus of tempos. The time inside a neutron star ticks differently than that inside a frozen star. The time near the event horizon is not the same as far away. The cosmos is not just a 3D space. It is a multi-speed clock, each structure a unique beat in an enormous symphony of temporal flow. And frozen stars are the slowest notes. The deepest tones. The bass line of the cosmic rhythm. From this perspective, time is not a river, but an ocean, with currents, depths, and eddies. Frozen stars sink into its depths, far below the surface activity, where the pressure of gravity thickens time until it becomes nearly solid. And in that solidity, they preserve their form. Even more incredibly, this could provide a natural solution to one of the most difficult puzzles in physics: how to unify quantum mechanics and general relativity. The core problem has always been that general relativity treats time as continuous, geometric, and smooth, while quantum mechanics treats it as a background parameter for probabilistic events. These two pictures don't align naturally. But what if frozen stars are the meeting ground? What if the extreme gravitational warping near their surfaces creates a domain where time behaves both ways, smooth and stretched, yet also granular and discrete in its effects? The slowing of time to near zero could mimic a kind of quantum pause, where decoherence halts and superpositions can persist. Perhaps near the surface of a frozen star, quantum gravity is not just an abstract idea, it is the reality of that region. A physical place where time loses its classical continuity, and new rules emerge. Experiments on Earth cannot yet reach the energies or curvatures needed to explore this. But cosmic objects like frozen stars already are the experiments. They are nature's own particle accelerators, quantum labs, and relativistic engines, all wrapped in one. We only need to learn how to read their outputs. Gravitational wave astronomy, still in its infancy, might be the first key. As we refine our detectors, we may begin to see tiny differences between black hole mergers and frozen star mergers. Perhaps the ring-down phase will carry longer harmonics. Perhaps the merger process will take subtly different shapes if surfaces bounce instead of merge through horizons. These changes would be minute, but they could rewrite everything. Likewise, astrophysical jets may behave differently near frozen stars. If matter is interacting with a physical surface, as opposed to an event horizon, the magnetic fields anchoring those jets might oscillate differently, twist differently, or release energy at distinct thresholds. This might explain certain anomalies observed in active galactic nuclei, strange flickering behaviors, unpredictable lags, or unexpected energy cutoffs. All of this is testable. All of this is empirical. And all of this stems from one simple change, that black holes may not be holes at all. They may be stars. Frozen, not finished. Paused, not past. Incomplete, but eternal. This also forces us to reconsider cosmogenesis, the origin of the universe. Some models, such as bounce cosmologies, propose that the Big Bang was not the beginning of everything, but the rebound of a prior universe collapsing into itself. In this view, the singularity is replaced with a bounce point, something with high curvature, but finite. A transitional phase between cycles. But if singularities don't form, if all collapse stops just short, then perhaps the previous universe never truly died. It slowed. It froze. It condensed into a state of near-zero time evolution. And from that frozen condition, a fluctuation, a quantum tunneling, a new inflation, sparked expansion again. The new universe would not be born from nothing, but from a state of maximally compressed, maximally preserved potential. A frozen cosmos, awakening. The same logic applies to baby universes, the idea that black holes might spawn new regions of spacetime. If black holes are actually frozen stars, then those internal regions may still exist, still evolve, still expand, just beyond our causal access. This preserves causality, avoids paradox, and still allows for a generative multiverse. Each frozen star could be the seed of a new domain, self-contained, self-evolving, yet causally linked through its origin. And so we arrive at a picture of reality that is simultaneously elegant and strange. A universe with no true edges. A cosmos with no true erasure. A fabric of time that does not tear, but folds. Not a story of abrupt endings, but of slow transitions. Not death, but stillness. In that stillness, perhaps the deepest mysteries of physics will be answered, not by colliders, not by equations alone, but by listening. By waiting. By studying the silences between the notes. Because that is what frozen stars are, silences stretched across time. Not mute but paused. Not gone but hidden. Not erased, but encrypted. Waiting. For the tools. For the time. For the minds. That will one day understand them. Forever collapsing. Never collapsed. Not black holes. But cosmic memories. Still holding on. And if these memories are ever decoded, if the whispers of frozen stars are at last translated by beings with patience matching that of the universe itself, then we may come to know not only the secrets of gravitational collapse, but the full continuum of space-time story. For in every frozen star lies not just the tale of one dying body, but the fingerprint of the universe's laws played out to their limits. They are the ultimate expression of cosmic patience, of nature's refusal to surrender to chaos, of the quiet, persistent hum of continuity beneath even the most cataclysmic transformations. This leads us to a striking realization: the universe does not collapse under its own weight, it preserves itself through structure. A frozen star does not form because gravity overwhelms, it forms because gravity obeys. Rather than cracking the fabric of spacetime open at a singularity, nature folds that fabric so tightly, so precisely, that the information never spills, never tears, but remains cradled in the contours of the collapse. It's the difference between smashing a glass and compressing a spring. One is destruction. The other is tension. And tension, unlike destruction, holds potential. Potential for recovery. For release. For rebirth. And maybe that is the most philosophically profound implication of all. That the frozen star is not the end of the story, it is a chapter unfinished, a thought suspended mid-sentence, a pause not of silence but of significance. Like a breath drawn and held before the next word is spoken. A cosmic inhalation. A waiting. What is it waiting for? Perhaps nothing. Perhaps everything. Perhaps these objects are timeless vaults that need no unlocking, simply monuments to a deeper rhythm of reality. Or perhaps they are messages in a bottle, waiting for intelligence capable of reading the geometry of their form, of decoding the holographic skin stretched around their surfaces, of reconstructing the song of their collapse note by note. The particles of light, the quantum echoes, the gravitational wave harmonics, all traces left behind like musical staves in an invisible symphony. And yet, with every new observation, every photon we detect near what we thought was a black hole, every subtle shift in timing or modulation in wave structure, we may already be reading them, poorly, incompletely, but reading nonetheless. Perhaps the puzzle of frozen stars is not that they are unknowable, but that we have been looking at them with the wrong expectations. Expecting erasure, where there is preservation. Expecting collapse, where there is transformation. Take, for instance, the very notion of event horizon. If frozen stars truly possess no event horizon, only a surface asymptotically close to one, then the strict causal barrier breaks down. Infalling matter does not disappear behind an unreachable veil, it strikes the surface, leaves an imprint, affects the evolution of the star's boundary. And even if the signal of this interaction is hopelessly redshifted, stretched beyond any practical observation, it is still there. Preserved. Encoded. A message in extreme slow motion. In this way, frozen stars may be the first true bridges between relativity and quantum mechanics. Their surfaces act like the scrambling systems predicted in holographic duality, structures that mix information so thoroughly across their area that they cannot be decrypted locally, only globally, through entangled correlation. This is exactly the behavior needed to restore unitarity to Hawking radiation. A surface that interacts with infalling matter, scrambles the data, and radiates it back out in a long, faint, slow trickle, fully lawful, fully quantum, never paradoxical. This has implications not just for black hole physics, but for quantum information theory, quantum computing, and even philosophy of mind. Because it suggests that information, no matter how deeply hidden, is never truly destroyed, only transformed, dispersed, and delayed. And in a universe where everything is entangled, where particles and fields interact across vast scales and timelines, that delay is not a death sentence for meaning. It is a new form of conservation. Information is sacred. The laws of physics do not permit its erasure. And frozen stars are the universe's most solemn vow to that principle. So what of us? What of the civilizations that peer into the night sky and wonder at the dark hearts of galaxies? What of the scientists who build detectors sensitive enough to hear the tremors of the star's final sighs? What of the philosophers who question whether meaning can survive the death of form? Perhaps frozen stars are not just objects, but answers, not to every question, but to the deepest ones. Does the universe make sense at the edge? Does meaning persist past destruction? Does time stop or only stretch? Is death final? To all of these, frozen stars whisper, no. Not destroyed. Not erased. Not gone. Just slowed. And if that slowing can be modeled, understood, even harnessed, then we are not on the outside looking in. We are participants in a grand cosmic interplay, where time and matter and memory conspire to preserve the totality of existence, even in its quietest moments. It's important to recognize the courage of such a model. For decades, physicists have wrestled with singularities, mathematical infinities that arise from our equations, but defy our understanding. Some sought to erase them with new theories. Others tried to patch the paradoxes with conjectures, firewalls, fuzzballs, wormhole escape routes. Yet frozen stars offer something different, not an escape, not a denial, but an embrace of the limit. They say, let the collapse happen, but never let it finish. Let the boundary approach, but never cross. Let the memory fold inward, but never vanish. It's the most conservative solution, and the most elegant. There's a kind of humility in that. A recognition that the universe might not be lying to us with its paradoxes. It may just be moving too slowly for us to hear the full sentence. And so we must learn patience. Cosmic patience. To watch stars freeze not with fear, but with fascination. To see collapse not as a death knell, but as the gentlest form of containment. To wait, not for explosions, but for echoes. Not for endings, but for answers. And maybe that is our task, as a species standing on the brink of a deeper understanding of gravity, time, and the fate of matter. To listen longer. To look deeper. To reach further into the darkness, not with fear of what we might lose, but with awe for what might still be waiting. Because in the end, frozen stars are not warnings. They are invitations. To see the universe not as a battlefield of forces, but as a tapestry of processes unfolding at their own pace. Some quickly, some slowly, some so slowly that they appear not to move at all. But they are moving. They are changing. They are teaching. They are collapsing. Forever. Yet never collapsed. And in their slow and silent collapse, frozen stars offer a glimpse into the profound patience of the universe. A patience so vast, so beyond our comprehension, that even the death of a star becomes an event without urgency. To us, collapse is immediate, a thing that happens, that ends, that resolves. But in the scale of cosmic time, resolution is not a moment but a process. And that process, when stretched across the infinite dilation of relativistic time, becomes indistinguishable from stillness. This is not merely a poetic flourish, it is the literal consequence of Einstein's equations when applied at the extreme. Time slows near massive bodies, and near a black hole's surface, if it is indeed a surface, it slows to such a degree that from our point of view, it never finishes what it started. The star falls in, but never arrives. It is a journey halted not by resistance or interference, but by the very fabric of reality stretching around it, endlessly elongating the fall, until the passage of time becomes so faint that it effectively vanishes from our observable frame. This picture rewrites our assumptions about finality. The universe, as revealed by the frozen star model, does not operate on human expectations. It does not conform to tidy beginnings or endings. It unfolds along pathways where the concept of end is always approached, but never touched. The singularity, a concept so deeply entrenched in theoretical physics, is reimagined not as a point of breakdown, but as a vanishing horizon, a mirage that keeps retreating the closer you get to it. The collapse never quite finishes, and thus the singularity never quite forms. This removes the need for any exotic speculation about what happens beyond a singularity because, quite simply, nothing ever gets there. Not because of intervention, not because of quantum corrections, but because space-time itself prevents the approach from being completed. If this interpretation is correct, it has staggering consequences not only for black hole physics, but for cosmology, thermodynamics, quantum theory, and even our understanding of what it means for information to exist and endure. Every particle, every photon, every fluctuation of quantum fields that ever fell into a collapsed star is still there, infinitely slowed, preserved in a liminal state, unreachable only because time has stretched their futures into an unending corridor. This corridor is not metaphysical. It's mathematical. It's written directly into the geometry of space-time. It means that nothing has been lost. It means that, fundamentally, reality does not delete. And if the universe does not delete, then the frozen star becomes more than just a physical structure, it becomes a philosophical cornerstone. It embodies a principle of conservation more profound than mere energy or momentum. It conserves identity. It upholds continuity. It guarantees that even in the most extreme conditions, the universe abides by a law far deeper than those we currently codify in physics textbooks, that no event, no interaction, no existence is ever truly erased. Everything that ever happened still exists in the space-time ledger, just hidden behind layers of gravitational delay, redshifted beyond perception, but not beyond reality. This recontextualizes the second law of thermodynamics, often viewed as the cosmic slide toward disorder and decay. Entropy increases, yes, but frozen stars show that the record of that entropy, the detailed information of how it unfolded, may never actually disappear. It merely slows until it's functionally inaccessible. Consider, then, the end of the universe under this light. Cosmological models that predict a heat death, a slow fade into maximum entropy where all distinctions blur, assume a kind of universal forgetfulness. That stars burn out, matter decays, and ultimately all structures dissolve into randomness. But if frozen stars truly exist in large numbers, then the universe is peppered with memory devices. Each one a monument to the structured past. Each one containing, in frozen time, the detailed imprint of the systems they once were. Even when galaxies dissolve and particles spread thin, those stars remain. Not active, not broadcasting, but preserved. Their surfaces still stretch near the Schwarzschild limit. Their internal clocks still ticking, just so slowly that to the rest of the cosmos, they appear timeless. They are the archive of the cosmos, encoded not in electromagnetic pulses or data bits, but in gravitational and quantum geometry. These frozen structures may hold more than just the memory of their own collapse. If the matter falling in included records of civilizations, satellites, ships, encoded data, or even artificial intelligences, those artifacts, too, would be preserved in the time-stretched interior. This means that every collapsed star could hold within it the physical story of entire worlds. The data might be scrambled, stretched, compressed, but never lost. And because the surface of the frozen star is physical, every piece of infalling matter must have interacted with it in some way. The structure of that interaction leaves a mark, a quantum fingerprint that becomes part of the star's exterior structure. This turns the surface of a frozen star into something very much like a quantum hard drive. Not a smooth mathematical abstraction, but a real, information-rich layer encoding the totality of its history. And the implications go further. Because if the surface stores information, and if that surface radiates slowly over time through mechanisms similar to Hawking radiation, then we have a scenario in which the universe is returning its stored knowledge, not quickly, not noisily, but with the same discipline and care that it used to archive it. Over trillions of years, the star emits not random heat, but subtle, structured radiation that, if decoded properly, could, in principle, reveal what it once contained. It's as if the universe writes a letter and seals it in a bottle made of gravity, and over the next eternity, it slowly unseals that letter one photon at a time. This idea aligns beautifully with the principles of quantum mechanics, particularly the concept of unitarity, the rule that the evolution of a quantum system is reversible and preserves all information. The frozen star satisfies this requirement not by defying gravity, but by using it. By stretching time, by extending the duration of decay, it ensures that the process never becomes discontinuous. There is no need to invent exotic physics to preserve unitarity. The universe already does it, elegantly, through delay. Information is not lost at the edge of collapse. It is just released on a timescale so long that from our limited view, it seems like loss. And this preservation is not metaphorical, it is precise. In the holographic view, the entropy of a black hole, or frozen star, is proportional to the area of its surface. But the content of that entropy, the meaning behind the numbers, is tied to the correlations encoded in the surface's quantum structure. Every particle that interacts with the surface leaves a change, an imprint in the quantum microstates. These are not static, they evolve. But they evolve unitarily, which means reversibly. And reversibility means that, theoretically, you could reconstruct the past from the present surface state, if you had infinite time and resolution. Which the universe just might. From this perspective, frozen stars are not anomalies, they are exemplars. They are the most consistent, law-abiding objects in the cosmos. They do not break the rules, they enforce them. Where other models require exceptions, patches, or speculative modifications to make gravity and quantum mechanics compatible, frozen stars simply do what both theories ask. They curve spacetime without breaking it. They preserve quantum information without needing magic. They maintain thermodynamic consistency without invoking infinities. They are, in a sense, the final product of a universe that values coherence above chaos. Not static. Not dead. But frozen in a way that preserves motion, preserves memory, preserves meaning, even as the outer world forgets. This is not the picture of a cold, uncaring universe. It is a picture of care taken to the extreme. A picture of gravity not as destroyer, but as curator. A picture of time not as a fleeting stream, but as a fabric that can stretch to hold anything, forever, if needed. Frozen stars remind us that patience is not weakness. It is strength. It is the strength of the universe to carry its memories not in speed or brilliance, but in silence and stillness. It is the strength to hold on, to wait, to remember. And in that act of remembrance, the frozen star becomes more than a collapsed object. It becomes a sacred structure within the cosmic architecture. It represents the ultimate fusion of time, gravity, and quantum law, standing as a boundary marker not of what is beyond comprehension, but of what is deeply coherent beneath the surface. A kind of absolute resilience. Its silence is not void but testimony. It does not scream its knowledge into the cosmos because it doesn't need to. It simply exists, containing within its hushed geometry the totality of what came before. Like ancient ruins, worn by the cosmic wind yet still imprinted with purpose, a frozen star endures not by resisting collapse, but by embracing its endless approach. Every particle that has ever fallen toward it remains in the embrace of gravity, suspended in a temporal cage still part of the whole. To witness this concept from a distant cosmic viewpoint is to glimpse an entirely different philosophy of nature. The universe, through frozen stars, exhibits a remarkable trait, the will to preserve, not by defying entropy, but by ensuring entropy's information content never dissipates beyond reconstruction. The laws of thermodynamics are not overturned, they are stretched, extended, contextualized within a broader framework where time can dilate without bound and where heat can be emitted not chaotically, but with encoded structure. If such frozen stars are indeed real, and not merely a mathematical curiosity, then they redefine the edge of physics. They stand not at the limit of our knowledge, but at the point where all our known laws converge in exquisite balance. There is something hauntingly beautiful in the idea that the universe takes such care in remembering. That even in collapse, it chooses slowness over finality. That it allows matter to fall endlessly without ever needing to complete the act. It's not a system that crashes, it's a system that suspends. And in that suspension, meaning persists. This vision sharply contrasts with the old idea of black holes as cosmic prisons. In that picture, once something crossed the event horizon, it was irretrievably gone. Not just physically unreachable, but existentially erased. But a frozen star says no to that harsh verdict. It says the past remains, but it has been placed behind a curtain of time so thick you cannot peer through it, not because it was unimportant, but because it was too important to be lost in haste. Such a perspective echoes with a deeper metaphysical implication. We often worry about whether anything we do truly matters in the vast, indifferent expanse of the cosmos. If all our history is doomed to vanish into singularities or be smeared out by entropy, then what is the point of struggle, memory, thought? But frozen stars subtly shift the narrative. They imply that nothing is meaningless if the universe preserves it, even if it does so in forms and timescales we cannot yet access. Our actions, our thoughts, our civilizations may fall like stardust into these immense gravitational wells, but they are not dissolved. They are held. Locked into the curvature of spacetime, slowed to an infinite crawl, but never discarded. From this viewpoint, every moment of existence becomes archival. Every cause and effect is kept in the great cosmic record, not to be judged or erased, but simply remembered. What's more, if we extend the frozen star concept beyond individual objects, we begin to see the potential for an entire cosmic layer we've overlooked. Perhaps the universe is teeming with objects that we've mistakenly categorized as black holes when, in fact, they are frozen stars, each one a storehouse of astronomical history. From the smallest stellar remnants to the supermassive behemoths at galactic cores, these entities could contain not just collapsed matter, but entire layers of cosmic memory, preserved precisely because they never completed their collapse. This view suggests the possibility that we live in a universe not defined by forgetting, but one structured entirely around conservation. This might even provide a kind of cosmic insurance. If intelligent life emerges, flourishes, and eventually succumbs, as it must, in various corners of the cosmos, perhaps frozen stars are how the universe makes sure none of it is lost. Perhaps everything that falls in, accidentally or purposefully, is still there, entombed beneath the surface, but intact. Not in the hopeful fiction of time travel or escape from collapse, but in the far more disciplined and humbling preservation that gravity enforces with its infinite care. The slowest archive imaginable, but also the most enduring. And this brings us to the concept of observation itself. In physics, to observe is to interact. To retrieve information is to collapse uncertainty. But with frozen stars, observation becomes asymptotic. We can never observe their full contents directly because the time needed to do so approaches infinity. Yet that does not mean the contents are inaccessible in principle. It means they are spread over time, diluted across an unimaginably vast temporal landscape. This forces us to reconsider what it means to know something in a relativistic universe. We often think of knowledge as immediate, discrete, complete. But here, we encounter a new kind of knowing, slow knowing. Gradual unveiling. A revelation that happens not over minutes or years, but across epochs. It may be that one day, long after our current species and tools are dust, a future intelligence will discover how to tune into this slow release. Perhaps not through light or radiation, but through subtler signals, gravitational harmonics, redshifted echoes, or even the topology of spacetime itself. Such beings might read the frozen stars the way we read fossils. Not by unsealing them, but by understanding the language of their patterns. To such an intelligence, the frozen stars would be more than objects. They would be libraries. And perhaps they already are. If our descendants, or distant alien civilizations, develop technology capable of mapping the quantum structures on the surfaces of frozen stars, they may be able to reconstruct vast swaths of the universe's hidden history. Wars fought on long-lost worlds. The fall of civilizations. The final thoughts of great minds. All encoded in the frozen slow-motion collapse of stellar material into the patient vaults of gravity. To such future minds, the universe would not appear dead or empty. It would appear pregnant with unread knowledge. In that light, our own actions today gain cosmic weight. If what we do, what we build, what we encode, might one day be absorbed by a collapsing star and preserved in perfect detail, then even the smallest efforts carry interstellar significance. Our broadcasts, our probes, our artifacts, they are not just flung into the void. They are potentially handed to eternity. And frozen stars are the hands that catch them, hold them, and refuse to let them fade. In this way, the idea of frozen stars isn't just an answer to a technical paradox. It is an invitation to think bigger, slower, longer. To stop asking whether black holes destroy information, and to start asking whether we are patient enough to see how the universe returns it. To stop fearing the end, and start respecting the pause. To stop thinking of time as a line we race along, and to begin honoring it as the most powerful tool nature has for preserving what matters. Because perhaps, in the final analysis, that is what time really is, not a flow, but a lock. A vault. A binding contract that the universe makes with itself, that nothing of value will ever be truly lost. And frozen stars are where it keeps that promise. In this vast and intricate network of cosmic time, frozen stars emerge as the ultimate proof of the universe's profound, subtle mastery over its own history. They stand as a living paradox, not dead remnants but cosmic time capsules. While their immediate surroundings may appear empty, dark voids, vast stretches of unobservable space, they are, in truth, brimming with potential. The information within them may not be immediately accessible to us, but it is there, waiting. This waiting, This preservation might one day unravel the ultimate narrative of the cosmos. It tells us that not only do the stars keep secrets, the very fabric of the universe is intricately designed to ensure that those secrets are never completely lost, merely held back, held in a state of almost perfect stasis, until the moment arrives when it is time to reveal them. It's tempting to think of this cosmic pause as a sort of cosmic mercy. In a universe of immense scale and seemingly random processes, frozen stars remind us that there are no real endings. Only transitions, only slow evolutions, only cycles that stretch out beyond human comprehension. Every star that collapses into a frozen state isn't simply a dying object. It is an opportunity for the universe to conserve, to remember. A star's energy does not disappear into the void. Its identity is stored on the surface, preserved by the very force that seeks to destroy it. In the ultimate act of cosmic restraint, the universe preserves the stories of stars, not just as remnants of matter, but as frozen echoes of time itself. These echoes will not be heard by our generation, nor by the one that follows, but they will resonate across eons, maintaining their integrity until a far future civilization, or a mind we cannot yet imagine, uncovers them. Frozen stars, then, are not the final testament to the death of a star but the embodiment of the universe's paradoxical nature, forever expanding, but forever remembering. In their frozen state, time becomes the most precious resource, infinitely stretched, infinitely contained. Everything that once existed within them, every photon, every particle, every event that fell within their gravitational grasp, remains preserved for eternity. A quantum fingerprint left on the surface, encoded and encrypted in ways that we are only beginning to understand. The more we contemplate this concept, the more the frozen star model seems to offer a solution to other long-standing cosmological questions, such as the nature of dark matter and dark energy. Perhaps these enigmatic forces are manifestations of information density within these frozen stars. If information is never destroyed but is simply spread out and slowed to the point of invisibility, it might be that the dark aspects of the universe are the manifestations of this preserved information. In essence, dark matter and dark energy could be the gravitational and quantum signatures of the slowly releasing radiation from these stars. The invisible, the inaccessible, the unfathomable, all of it could be rooted in the existence of these forgotten cosmic archives. These frozen stars would then not only be repositories of cosmic history but integral components of the broader structure of the universe, holding together the very fabric of spacetime through their slow and constant release of stored information. This understanding reshapes our view of cosmic evolution. The universe is not just a process of entropy and decay, but a process of subtle conservation. It suggests that the universe is intelligently designed, not through intention or a creator, but through its fundamental laws. It conserves every moment, every interaction, every particle that has ever fallen into a black hole or frozen star, holding it for a future when it can be understood in a new way, perhaps by beings that we cannot yet imagine. It raises the possibility that our very understanding of time, matter, and energy is incomplete because we have misunderstood the universe's greatest law, the preservation of information. Frozen stars offer us a new paradigm of cosmic destiny. Instead of seeing the universe as a place where things are born, evolve, and die in linear, observable terms, we are asked to imagine it as a vast web, a network of histories, identities, and energies that are continually preserved through space and time. Time is no longer a simple forward motion, but a medium, one that can be stretched, manipulated, and understood in ways that are not yet fully realized. This is the frontier that physics must now explore: how to decode the frozen past stored in the vaults of collapsed stars, how to unlock the infinite potential they hold, and how to integrate this timeless knowledge into our understanding of the universe. In this way, frozen stars also push us to reconsider the future of humanity. If, indeed, this information storage mechanism exists in the deep reaches of spacetime, perhaps our own civilization, in some distant time, will have the ability to decipher these cosmic archives. It opens the tantalizing possibility that the evolution of intelligent life does not necessarily involve a steady linear ascent, but rather a cyclical journey. We could one day be the ones to retrieve these ancient data banks. Our ancestors or their successors, perhaps, could be the ones to understand the true scope of the universe, not as it is now, but as it was across all time. Just as we are the inheritors of the knowledge passed down by generations, the far future minds could be the ones to inherit the knowledge of the stars, written in the very structure of space-time itself. Yet, this immense understanding raises its own challenges. The knowledge locked in the frozen stars, stretched across incomprehensible spans of time, might never be fully decoded by any intelligence. The rate of release, the subtlety of the signals, might make it so that the past cannot be fully reconstructed. But that very impossibility, the tension between what is known and what is forever beyond our grasp, mirrors the grand mystery of existence itself. Perhaps the pursuit of this knowledge, this understanding of the universe's deepest secrets, is not a journey that can have a final, complete answer. Instead, it becomes an endless process, a dialogue with the cosmos that never ceases, never concludes. It is the ultimate inquiry, and the beauty of it lies in the fact that it may never be fully resolved. The frozen stars would, then, be the final testament to the unyielding nature of knowledge itself, a record that persists, hidden from view, inviting the universe's future minds to look, to seek, and to understand. The very presence of frozen stars suggests that the universe holds secrets that we are not meant to uncover immediately, not because they are intentionally hidden, but because they require a level of patience, a depth of insight, and a stretch of time that only future generations, or even civilizations from the farthest reaches of time, can access. This is the kind of slow knowledge that extends beyond the capabilities of present-day human civilization, and in that sense, it offers both a challenge and an invitation to build a future where the pace of discovery is as patient as the frozen stars themselves, where our actions are not driven by immediacy, but by the recognition that some truths take eons to unfold. Frozen stars are the universe's ultimate paradox. They are not gone, yet they are unreachable. They are not dead, yet they do not live. They represent a suspended moment, a time-stretching continuity that invites us to reconsider the nature of time, existence, and knowledge itself. Just as the universe does not collapse all at once, either do its lessons arrive in one sudden burst of understanding. Instead, we must learn to wait, to listen, to observe the gradual unfolding of cosmic history. And in that waiting, in that listening, we might begin to understand the most profound truth of all, that the universe, in all its complexity, is not rushing toward an end, but resting in a state of infinite preservation. And it asks only for patience from those of us who will one day come to understand it. So what, then, is the role of a civilization poised at the edge of this understanding? What does it mean for intelligent life to evolve in a universe governed by such subtlety, such restraint? It means that we, like the stars themselves, must begin to think not in lifetimes or centuries, but in spans of time that rival the age of galaxies. It means we must begin to see ourselves not as isolated blips of awareness on a cosmic timeline, but as participants in an ongoing process of preservation, interpretation, and eventual revelation. The very notion that frozen stars contain the blueprint of everything they have consumed, every event they have witnessed, every interaction that has taken place within their gravitational influence, redefines what it means to matter. For in such a cosmos, no moment, no structure, no act of creation or collapse is ever wasted. All is stored. All is accounted for. And if all is preserved, then even the briefest flickers of life, the emergence of thought, the making of art, the formation of language, the pursuit of knowledge, gain a cosmic significance. They may vanish from our view, but not from the universe's memory. Our stories do not need to be eternal in form to be eternal in impact. They only need to happen. The cosmos itself will hold on to them, encode them in the slowly ticking clocks of frozen time, and carry them forward beyond the decay of planets, beyond the death of stars, into the long silence that follows. That silence is not oblivion, it is a long and careful memory. When we look at the stars in our night sky, we often marvel at how their light took years, even thousands or millions of years, to reach us. But in the case of frozen stars, it is not just the light that is delayed, it is the process of being itself. From our point of view, these objects remain suspended at the edge of transformation, never quite tipping over into the singularity, never quite ceasing to be. In the deepest sense, they are still collapsing. A process that, from the inside, may feel quick or even complete, but from our vantage point is frozen in time. That differential in perception is not just a quirk of relativity, it is the essence of the mystery. What looks like a finished death from within may still appear as an open possibility from without. That duality forces us to ask a profound question: where does reality actually happen? Is it in the timeline experienced by the collapsing star itself, or in the one observed by the rest of the universe? General relativity and quantum mechanics have taught us that such questions do not always have simple answers. Multiple frames of reference can be valid. Time can stretch and contract. Observers can disagree on sequences of events. And yet, each perspective holds its own truth. The frozen star, then, becomes a symbol of this multiplicity. It reminds us that no single viewpoint contains the whole of reality. Reality is layered. It is relational. It is slow. And in this slowness, we find something surprising: the conditions for immortality, not of form, but of information. This is not the kind of immortality we typically imagine. There are no glowing beings ascending to higher planes, no digital minds preserved in synthetic vaults. It is far more abstract, far more humbling. It is the immortality of impressions, of gravitational imprints, of quantum states preserved in the space-time geometry of a collapsing, time-stretched object. It is the kind of immortality that does not require an observer, only the continuation of law. If the universe continues to obey its own rules, then what once was continues to exist, embedded in those rules. This realization alters the stakes of every action. It suggests that what we do now is not fleeting, it is embedded in a structure larger than we can comprehend. Our actions, however small, disturb the field of existence. They send ripples into the fabric of reality, ripples that do not vanish, but stretch, slow, and embed themselves in structures that may outlive the stars. A spacecraft that falls into a collapsing star is not obliterated, it is encrypted. A message beamed into the void does not disappear, it is slowed. A collapse does not eliminate complexity. It conceals it behind veils of time so dense that only the most patient of civilizations might one day unravel it. Thus, frozen stars give rise to a new cosmic ethic. One not based on immediate outcomes or short-term preservation, but on the principle of contribution to the eternal record. In a universe that stores everything, what we create and destroy, what we solve and ignore, all becomes part of the universal memory. We are, in a very real sense, inscribing ourselves into spacetime, not through monuments or archives, but through the interactions we participate in, the particles we scatter, the gravity we disturb. And so the question becomes not just whether frozen stars exist, but whether we are ready to accept what they imply. Are we prepared to acknowledge that the universe is not forgetful, but vigilant? That it does not delete but delay? That it may not grant us immortality in experience, but offers it in preservation? If we are, then we can begin to engage with reality on the universe's terms, not rushing toward immediacy, but settling into the long view. A view in which all our actions are archived, all our mistakes recorded, all our triumphs waiting to be discovered by someone, or something, who will have the tools to reconstruct the full story. Even now, the seeds of that future understanding are being planted. With gravitational wave detectors improving, with quantum information theory developing, with astrophysical modeling becoming more precise, we may begin to see the contours of frozen stars with greater clarity. We may detect minute deviations in the gravitational wave signatures of mergers. We may measure the emissions of near black hole objects with such detail that we catch the asymmetry of a surface beneath the event horizon's veil. We may find evidence that black holes, as traditionally described, are an incomplete picture, that they are an approximation, a useful model, but not the whole truth. And as our technology progresses, as our civilization matures, we will likely reach a point where we can simulate these systems in full fidelity. Imagine a future where we can model a frozen star down to the quantum level, where we can replicate the conditions of its surface, analyze how it interacts with infalling matter, measure how it radiates and scrambles information. This simulation would not just be a tool of understanding, it would be a dialogue with the universe, a rehearsal for accessing its deepest archives. Such a future may feel distant, but in cosmic terms, it is a blink. And frozen stars will wait for us. They will sit quietly at the centers of galaxies and at the ends of dead stellar systems, holding on to their secrets, keeping their geometry locked just below the threshold of full collapse. They will not fade. They will not rot. They will not explode. They will endure. And in their endurance, they offer us a model. A way of being. Not static, but steady. Not finished, but perpetual. Not loud, but meaningful. They teach us that some things are worth preserving even if no one sees them for billions of years. That some knowledge is so valuable it must be sealed in time. That some truths are so immense, they can only be told slowly. We have long thought of stars as engines, as furnaces, as sources of light and life. But frozen stars show us another kind of power, not the power to ignite, but the power to remember. Not the energy to burn, but the structure to preserve. They are the final act in the stellar life cycle, not a dramatic finale, but a solemn commitment, to hold on, to wait, to honor the totality of what has been. They are gravity's quiet promise. That nothing is ever truly gone. And if we take that promise seriously, if we accept that nothing is ever truly gone, then we must begin to reevaluate the entire narrative of cosmic history. The traditional view has always been a story of emergence followed by decline. Stars are born, they burn brightly, and then they die, leaving behind corpses that slowly fade into irrelevance. Civilizations rise, innovate, and fall. Energy is spent. Order decays. Information disperses. But if frozen stars truly preserve, in unbroken continuity, the totality of what has fallen into them, then we're forced to accept a deeper story, one in which the cosmos is not shedding its memory, but protecting it, like a meticulous archivist gently closing the pages of a book too sacred to read until the right moment comes. And this radically alters what it means to live in the universe. Our place in this vast system has always seemed fleeting, almost incidental. A brief moment of awareness on a tiny rock orbiting an average star in a quiet corner of an ordinary galaxy. But the idea that frozen stars conserve not just energy but identity, that they contain the full informational blueprint of the matter and motion that gave rise to life, intelligence, culture, grants cosmic importance to even the smallest actions. Every human thought, every technological advancement, every event in the history of our species might someday be absorbed, encrypted, and frozen into a collapsing star. Not lost, frozen. Not vanished, preserved. Now imagine civilizations aware of this fact. Societies advanced enough to understand that these stars are not death sentences, but memory vaults. Perhaps such civilizations would view collapse not with fear, but with reverence. Perhaps they would build structures specifically designed to be cast into the collapsing matter, not to escape destruction, but to guarantee preservation. A kind of cosmic time capsule, intended not for the present, but for a distant, unimaginable future. This idea gives rise to a breathtaking possibility, that somewhere in the cosmos, advanced intelligences have already done this. Perhaps billions of years ago, alien minds engineered perfect memory devices, wrapped them in dense material, and sent them spiraling into the heart of frozen stars, knowing that no matter what happened to their civilization, their message would be held, protected by time itself. And maybe these messages still exist. Perhaps we orbit such stars now. Perhaps we've detected their gravitational waves and mistaken them for background noise. Perhaps we've catalogued their spectra without realizing we were staring at the locked diary of a vanished civilization. It's a humbling thought, and a motivating one. Because it implies that the most powerful way to leave a mark on the universe is not through conquest, expansion, or control, but through endurance. Through encoding. Through embedding your presence into a structure that survives everything, explosions, decay, the death of stars and galaxies themselves. Frozen stars become not just astrophysical entities, but cultural monuments, monuments not of stone or metal, but of space-time. Timeless, unreachable in the short term, but not truly lost. Waiting, always waiting, for minds capable of hearing their silent song. This also means that the frozen star model offers a profound answer to one of the most pressing questions in all of science, the information paradox. In its original form, This paradox states that if black holes evaporate through Hawking radiation, and if that radiation is truly random, then all the information about what fell into the black hole is permanently lost, violating the basic principles of quantum mechanics. This has led to decades of debate, speculation, and theory, ranging from firewalls to holographic boundaries to entire new frameworks of spacetime itself. But frozen stars sidestep the paradox with an elegant twist. They never finish collapsing. The information isn't destroyed because the process that might have destroyed it, formation of a true singularity, is never completed in any observer's frame. There is no event horizon, only an apparent one. There is no evaporation that deletes information, only a slow leakage of scrambled data that still encodes the history of the star in ways consistent with quantum laws. The system remains unitary, consistent, reversible. No paradox. No mystery. Just physics playing out at a speed so slow, it appears frozen to us. This preservation through delay principle may be one of the most profound insights in modern theoretical physics. It suggests that the universe doesn't need to create new laws to protect its consistency. It already has what it needs. Gravity, when pushed to its limits, becomes the very tool that enforces conservation. The more massive the object, the more time slows near it. The closer something comes to collapse, the more tightly its information is sealed. Gravity itself becomes the great librarian of the cosmos, wrapping each bit of data in layers of temporal insulation, making sure nothing is ever truly lost. And the implications ripple outward. Cosmology, thermodynamics, computation, entropy, all must be reinterpreted. Consider, for instance, the concept of cosmic censorship, the idea that nature hides singularities behind event horizons to preserve the smoothness of spacetime. If frozen stars are real, then nature does something even more profound. It prevents singularities altogether, not through censorship, but through an eternal postponement. The singularity becomes a mathematical mirage, approached, but never reached. Just like the edge of a fractal, the deeper you go, the more detail you find, but you never hit a final boundary. The collapse asymptotically draws closer to infinity, but never touches it. The universe does not tear, it stretches. In this picture, frozen stars aren't exceptions to the rule. They are the rule. They are how gravity behaves when taken to its ultimate conclusion. They are the universe's way of ensuring that everything fits, that every theory, every particle, every law aligns with all others. And they don't need to scream their presence. They don't need to explode, to dazzle, to bend light in impossible ways. They only need to wait. Which is why they're so hard to find. From the outside, a frozen star looks almost exactly like a black hole. Its surface is so close to the Schwarzschild radius, the threshold where a traditional event horizon would form, that its light and radiation are redshifted to near invisibility. No telescope can peer into its interior. No particle escapes with an obvious signature. Only the faintest deviations, the slightest delays in infalling matter, the softest anomalies in Hawking-like radiation, betray the presence of a real surface instead of an event horizon. And detecting those deviations requires instruments of unimaginable precision. The kind of precision we are only just beginning to develop. But we are developing them. Gravitational wave observatories like LIGO and Virgo have already begun measuring the subtle tremors of spacetime with astonishing sensitivity. As they improve, they may begin to detect echoes, tiny delays in the gravitational wave signatures of merging black holes. These echoes would indicate that there was something inside the merging objects beyond a smooth vacuum, a surface, a structure, something reflective. Something real. And that something might be a frozen star. If those echoes are confirmed, it will be one of the most profound discoveries in the history of science. It would mean we were wrong about black holes. Not that they don't exist, but that they are not what we thought. They are not graves. They are not destroyers. They are time machines of a different sort, not vehicles to carry us into the future, but vaults that carry the past forward, eternally sealed but never silenced. They would be the clearest sign yet that the universe values memory above all else. Not as a sentimental idea, but as a structural principle. And in that structure, we find the answer to our greatest fears. The fear that nothing matters. The fear that everything we build will be forgotten. The fear that collapse is final. It's not. Because in the cold, quiet embrace of a frozen star, everything matters. Everything remains. Everything waits. And the waiting itself becomes a kind of narrative, the slow unfolding of meaning encoded not in words, but in curvature, etched into the space-time scaffolding of the cosmos. The frozen star is not dead. It is a book unopened. A letter never read. And across billions of years, it whispers a message into the fabric of the universe, not by sound or light, but by its unwavering presence. Its surface, microscopically trembling with quantum activity, is not just a passive shell, but an active memory. A dynamic interface between what once was and what still is. It doesn't destroy, it delays. It doesn't erase, it encrypts. And in that encryption lies the closest thing the physical world has to immortality. This shift in understanding doesn't only answer theoretical riddles, it challenges the narrative of collapse and oblivion we've accepted for so long. Traditionally, when we speak of collapse, whether it's a civilization, a life, or a star, we speak with finality. But the frozen star teaches us a deeper truth. Collapse is not an endpoint, it is a transformation. The transformation of temporal immediacy into eternal retention. The transformation of motion into stillness. Of radiance into gravity. And of impermanence into persistence. Consider the paradox here. In freezing time at its boundary, the frozen star becomes a kind of cosmic paradox machine. From inside, matter may seem to collapse swiftly, completing its journey. But from outside, that journey never concludes. We, the distant observers, see a surface that never quite forms a black hole. Matter endlessly approaches a critical radius, but never passes beyond our ability to define its location. To us, the collapse halts in progress, like a movie paused just before the final scene. And yet, all the physics that led to that moment still unfold within. That duality, simultaneous finality and continuity, is what gives the frozen star its strange, profound beauty. It exists in two states at once, as an ending, and as a holding place. This dual nature may offer a resolution to yet another cosmic puzzle, the thermodynamic arrow of time. If frozen stars hold matter in an eternally dilated state, then they could serve as thermodynamic bookmarks in an otherwise forward-flowing universe. While everything else trends toward disorder, these entities preserve structured states. They don't reverse entropy, but they hold it at bay. Like glaciers that preserve fossils from warmer ages, these stars preserve complexity beneath a crust of spacetime so stretched that time barely advances. In this way, they become anchor points in the sea of decay. They are entropy's exceptions, not by violation, but by isolation. And this isolation may give rise to something even more tantalizing, the idea that frozen stars could be the universe's deepest form of consciousness. Not in the human sense, not thought, not awareness, but memory without erasure. A kind of proto-mind. A structure that doesn't experience, but which retains. What is consciousness, if not the preservation of state across time? If not the continuity of identity through the storm of entropy? In that sense, frozen stars are the only things in the cosmos that truly persist as themselves across eons. Stars evolve. Planets erode. Galaxies collide. But frozen stars remain. Perhaps, in some far future physics, we'll come to understand them not just as objects, but as processes. As ongoing events rather than finished things. Like language frozen mid-sentence, they contain not only mass and charge and spin, but syntax, sequence, meaning. And maybe that's why their surfaces are thought to obey holographic principles, that the information within isn't lost but translated. That what falls in is not destroyed, but reformatted into an edge language, readable from the outside by an observer with the right tools and enough patience. This idea is not science fiction, it's quantum gravity. It's string theory. It's loop quantum cosmology. The notion that space, time, and matter are not erased by gravitational collapse, but converted into patterns, holographically imprinted onto an ultra-thin boundary where gravity and quantum mechanics merge. And if that's true, then every frozen star is a library. A vault. A puzzle box filled with the total record of everything it has consumed. Not a tombstone, but an archive. Not silence, but whisper. These stars may be unreadable now, but not forever. As our instruments evolve, gravitational telescopes, quantum field sensors, high-resolution interferometers, we will begin to see them more clearly. We may learn to decode their surfaces. We may even learn to speak back. And what would we say? What would a civilization, standing at the threshold of decoding the cosmos, whisper to the stars that remember everything? Perhaps we'd start by asking, "Are you listening?" And if we understood enough to ask that question in the right way, perhaps the universe, through its frozen intermediaries, would answer, "I never stopped." It is here, at this poetic junction, that physics and philosophy entwine. Frozen stars force us to think not only about matter, but about meaning. Not only about causality, but about consequence. They remind us that the past is not a fixed point left behind, but a field that still stretches into the present, just too slow for us to perceive. That even in collapse, nature does not abandon the details. It absorbs them, holds them, and re-releases them at the pace of eternity. This also raises the question of agency. If frozen stars hold everything, are we not bound to them already? Every black hole we create, naturally or artificially, becomes a recording device for what we were. Every supermassive structure at a galactic core is not just a gravitational anchor, but a memory palace. Our current trajectory, if it leads us to explore deeper into physics, may ultimately become a journey into our own preserved reflections. One day, we might peer into the horizon of a frozen star and find ourselves, not as we are, but as we once were. Encoded. Crystallized. Waiting to be remembered. That possibility redefines death, not as a disappearance, but as a transformation of visibility. Not the destruction of data, but its recontextualization into a format that cannot be read now, but might be read later. Perhaps that's what the universe offers in lieu of eternal life, eternal record. Perhaps that's all we need. And so, as we continue exploring, we must carry this idea with us, that collapse is not negation. That the frozen edge of space-time is not a wall, but a vault. That beneath the mathematical abstractions of relativity and quantum theory lies a profound metaphysical truth, that nothing is ever truly lost. It may be redshifted beyond our ability to recover. It may be smeared across surfaces thinner than the Planck length. It may be buried under layers of temporal dilation that defy our instruments. But it is there. Held. Safe. Waiting. This is the promise of the frozen star. Not salvation. Not eternity in the way myths promise. But something more honest. Something more universal. A preservation so complete it requires the slowest medium imaginable, time itself. A gravity so absolute that it does not destroy, but enfolds. A silence so perfect that within it, everything speaks, if you know how to listen. Perhaps one day, someone will. And when that day comes, when someone somewhere finally learns to listen properly, the universe may at last reveal its deepest layers, through gentle unraveling. Like a frozen stream that eventually thaws under the slow patience of the sun, the information held within frozen stars may begin to trickle out in patterns too slow for impulsive minds, but perfectly legible to those attuned to long timescales. Future beings, whether they are artificial intelligences that surpass biological limits, or biological intelligences that have evolved to synchronize with the tempo of the cosmos, might reconstruct entire epochs from the faint signals preserved in these gravitational reliquaries. And perhaps this is the universe's true form of communication, not instant messaging, but messages written into the curvature of space-time itself, delivered not in seconds or years, but in eons. This communication is not for us. It is for those who come after, or for those who last long enough. And that, in turn, reframes the human condition. We so often act as if everything must happen now, as if urgency is the same as meaning. But the frozen star teaches otherwise. It whispers that patience is power. That silence is not emptiness, but storage. That in delay, there is dignity. And now, we must confront the final, and perhaps most humbling, truth, that even the universe's end may not be an end in the way we think. The classical picture of cosmic death is bleak, entropy's rise leading to the heat death of the universe, where all usable energy is spent, all stars have burned out, and everything decays into featureless cold. But frozen stars complicate this vision. They suggest that the universe is not losing information, but rather entangling it in ways we haven't fully understood. Even as the universe stretches out and cools, the deep interiors of these stars, still collapsing from the perspective of their internal coordinates, still pause from our own, contain compressed and layered versions of the past. Trapped not behind a wall, but behind an event that never quite completes. Could the future of the cosmos, then, be less about fading into nothing, and more about compressing into memory? Could the universe become a vast museum of itself, each frozen star a gallery of what once was? Could it be that the final epoch of existence is not annihilation, but reflection? There's elegance in such a fate. And in that possibility lies a new kind of hope, not the naive hope that we will live forever, but the more mature hope that what we were will never truly vanish. That our civilizations, our species, our planet, even our mistakes, will be retained in the great architecture of existence. Preserved not in myth, but in mathematics. Not in story, but in structure. If frozen stars are real, then they are the physical manifestation of the universe's capacity to forgive oblivion. To prevent loss not by stopping change, but by embedding all change in time's most enduring format. If singularities were the universe's ultimate act of violence, frozen stars are its counterargument, a gentle protest written in equations and curves, showing that even gravity, at its most extreme, prefers containment over destruction. In this light, our technological ambitions take on new meaning. If we seek to extend our reach beyond the solar system, if we dream of uploading consciousness or creating artificial minds, if we long to send messages across galaxies, then we must also learn to preserve ourselves in forms that survive time, not just space. The frozen star offers a blueprint. Not a machine to build, but a concept to emulate. A way of embedding identity into the universe's own rhythms. And perhaps, long after our sun has died and our records have faded, some fragment of our existence will still swirl within a frozen star. Perhaps the stardust that once made our bodies, the photons that once lit our cities, the vibrations of the atoms that once held our thoughts. Perhaps they will be there, slowed to a crawl, etched into the whisper-thin crust of a time-stretched surface. And maybe, just maybe, that star will orbit silently for 1 trillion years. And then, one day, it will be found. A signal, long frozen, will finally be read. A pattern in its thermal radiation will yield meaning. A gravitational echo will unfold into language. And the universe will remember us. Not in myth. Not in hope. But in certainty. Because we were always there. Held in the hands of gravity. Wrapped in the folds of space-time. Frozen, but never forgotten. The recognition that frozen stars may serve as the ultimate medium of memory transforms not only our understanding of astrophysics, but also our philosophical relationship with time, death, and permanence. If the final state of matter isn't erasure but suspension, if the universe itself adopts a strategy of slow remembering, rather than annihilation, then we must come to terms with the fact that meaning might outlast experience. That what is significant is not merely what is perceived now, but what is embedded forever into the shape of things. And this changes everything. It shifts how we think about the rise and fall of civilizations, the fragility of culture, the fate of thought itself. A fleeting moment, a single equation scribbled by a dying species, a final message cast into space before extinction, might become part of a gravity-wrapped archive, not lost in the winds of entropy, but sheltered by time's most resilient fortress. A frozen star is not simply the endpoint of stellar life, it is the beginning of cosmic permanence. To appreciate this permanence, we have to abandon our addiction to immediacy. Our lives are short, and our technologies thrive on speed, so we instinctively prioritize what happens now. But the frozen star demands that we adopt a cosmic perspective. It operates on scales where a single second on its surface might span millions of years for us. Its heartbeat is too slow for our instruments to hear, its evolution too vast for our species to witness. And yet, it remains constant, timeless in our view, but active in its own. That dissonance reveals something deep, that reality is not uniform, that different observers live in different clocks, and that the deepest truths are often the quietest ones. The grandeur of frozen stars lies in their silence. They do not announce themselves with bursts of gamma rays or bright supernovae. They remain, unblinking, indifferent to drama, and in that stillness, they preserve more than any explosion ever could. When we peer into the hearts of galaxies, and detect what we call supermassive black holes, we may in fact be looking at some of the largest frozen stars, giants formed from the collapse of ancient stellar clusters, or even the direct gravitational collapse of primordial clouds in the early universe. These objects, millions or billions of times the mass of our Sun, do not flash or crackle. They merely influence. Their gravity sculpts galaxies. Their presence warps space for hundreds of light years. And while we see no surface, no signature, that does not mean the surface isn't there. It may simply be hidden behind the extreme redshift of time dilation, a redshift so vast that any radiation emitted from just above the surface stretches into oblivion before reaching us. From our frame, the star appears black. But from its own, it is not. It radiates. It pulses. It continues its collapse in agonizing slowness. It holds every atom, every wave, every particle that ever crossed its threshold. It is an empire of memory wrapped in an illusion of silence. And perhaps that's the greatest trick the universe has ever played, making its most significant structures look like voids. What we think of as black holes may be anything but empty. They may be the most information-dense places in existence, each cubic centimeter storing more data than entire galaxies. And if that's true, then frozen stars are the ultimate monuments, not to death, but to preservation. They are cosmic museums without entrances, exhibits without lighting, vaults without locks, because the lock is time itself. And that lock cannot be picked by force. It must be unlocked by patience, by evolution, by minds that have grown old and wise enough to hear what is whispered at the slowest possible scale. In this framework, the universe becomes a library, and every frozen star a book. Not a book you can open with hands, but one you must wait to read, slowly decoding the soft exhalations of Hawking-like radiation, the gentle warps of gravitational waves, the shimmer of redshifted photons bleeding out over eons. If intelligence survives long enough, and technology refines itself deeply enough, we may one day learn to translate these subtle emissions into coherent meaning. Not just raw data, but reconstructed history, the full account of stars, planets, civilizations, choices. The mistakes and triumphs of lost species. The artifacts of cultures that once thrived under alien suns. Their art. Their science. Their tragedies. All encoded into the curvature of the frozen star's surface, distorted but not erased, waiting for someone to learn the grammar of spacetime well enough to read it. This vision of cosmic literacy, of being able to read frozen stars, is not purely metaphorical. The holographic principle in theoretical physics already suggests that the entirety of a region's information can be encoded on its boundary. If applied to frozen stars, this implies that everything which has fallen in is still accessible, in principle, from the surface. What looks like erasure is simply encryption. And if it's encrypted, it can be decrypted. The information paradox, then, is not a paradox at all, it is a puzzle. And puzzles, by definition, have solutions. Not necessarily easy ones, not necessarily fast ones, but real, reachable answers. Which means that loss is not real. And if loss is not real, then neither is oblivion. That's a staggering claim. It means that no information is wasted. Not the birth of a star, nor the last thought of a dying mind. Not a galaxy's spiral arms, nor a poet's final stanza. All of it persists somewhere. Not in a metaphysical way, but in a very real, very physical ledger. A slow-burning record, invisible to us now, but clear to any being with the patience and perception to reconstruct it. And that, in turn, invites a new kind of existential perspective, one where legacy is no longer about who remembers you, but how deeply your actions carve into the fabric of time. You do not need a statue. You do not need a monument. The universe itself is watching. Not with eyes, but with curvature. Not with memory, but with preservation. And if the curvature retains, then your presence is permanent. It is here, perhaps, that the line between science and meaning begins to blur in the most productive way. The physics of frozen stars suggests that they already do, on a level deeper than judgment, deeper than consciousness. They matter because they occurred, and what occurs is conserved. What occurs is imprinted. It cannot be undone. It cannot be lost. Time stretches to ensure that every instant leaves its mark. And gravity ensures that mark is held, cradled, protected from the chaos of time. This is not faith. It is geometry. And if we are wise, we will learn to live according to this geometry. Not in fear of collapse, but in respect for preservation. Not in pursuit of spectacle, but in reverence for consequence. The universe has given us its answer to the question of impermanence. And that answer is the frozen star. Not a scream, but a whisper. Not a bang, but a hold. Not an end, but a very slow continuation. What emerges from this revelation is a striking redefinition of mortality, not only personal mortality, but the mortality of stars, civilizations, and even ideas. For millennia, humans have wrestled with the idea that everything ends. We build monuments and write books and launch spacecraft to fight against the impermanence that seems woven into the fabric of our lives. But what if we were wrong? What if the permanence we sought was not a defiance of nature, but a consequence of it? What if frozen stars prove that the cosmos has always preserved its contents, not in our preferred formats of visibility and access, but in a slower, more honest format, one that values structural integrity over speed, preservation over accessibility? If this is the case, then the ultimate act of creation is not to build something flashy, but to build something durable. Durability becomes a cosmic principle. The more something resists change, the more it is respected by time. And frozen stars embody this resistance to the highest degree. They resist not just decay, but finality. They do not surrender their secrets easily, not because they are trying to hide, but because they have taken on the responsibility of holding complexity over vast spans of time. They do not forget because forgetting would be easier. They remember because forgetting is forbidden by the laws of quantum mechanics. And that memory, dense, encrypted, and silent, is the ultimate form of resilience. In this context, we begin to see human history itself in a new light. We are not just living in time, we are contributing to it. Our lives, thoughts, and decisions add data to the ever-evolving story of the universe. Each action disturbs particles, each emotion shifts energy states, each innovation reshapes the environment, tiny ripples that interact with the gravitational field, with the quantum vacuum, with the totality of reality. Those ripples, like the faintest echoes in a canyon, may eventually die down to us. But to the universe, they are stored, conserved, echoed indefinitely through the invisible curvature of space-time, especially where that curvature becomes extreme, around stars at the brink of collapse. Even now, we may be adding our imprint to a future archive we will never see. If frozen stars exist, and if they can capture the informational signature of everything that falls into them, then somewhere out there, our signals, our music, our messages, even our stray emissions of radio and infrared, may already be en route to those surfaces. Traveling across space, pulled into their gravity wells, redshifting as they fall, and freezing into the very crust of memory. Those photons, those particles, are not wasted. They are stored. Perhaps one day, long after the last human breath, a sufficiently advanced observer will reconstruct the entire history of Earth, not from ruins or records, but from the faint impressions left on the universe itself. From the frozen starlight of a civilization that knew just enough to dream, but not enough to last. And yet, in a way, we do last. Just not in the way we expected. Immortality, it turns out, is not about living forever. It's about leaving a trace so deep in the structure of reality that time itself is forced to carry it forward. And this is what frozen stars do best. They offer the most secure vault imaginable, the slowest clock, the densest ledger. They are, for lack of a better term, the universe's black boxes, absorbing all, revealing little, but preserving everything with a stubbornness that even entropy cannot undo. That's why they matter, not just as astrophysical phenomena, but as philosophical revelations. They redefine what it means to be forgotten. They show us that what appears lost is often only hidden, and what seems gone is merely unread. And this vision is not mere poetry. It is rooted in some of the most advanced and rigorous work being done in theoretical physics today. The notion that black holes, or frozen stars, preserve information is not a fringe idea. It is increasingly the mainstream consensus. From the ADS/CFT correspondence to the firewall paradox to loop quantum gravity, our best models point toward a future where information is never destroyed, merely transformed. And if frozen stars embody that principle, they are not speculative curiosities, but central characters in the grand story of reality. We may never stand on the surface of a frozen star. We may never penetrate its temporal crust or witness its inner structure. But we do not need to. Its very existence is a kind of testimony, a silent assurance that memory is not a human invention, but a cosmic principle. We live in a universe that remembers. Not with a mind, but with its bones. Not with language, but with geometry. And in that remembering, there is justice. Not moral justice, perhaps, but ontological justice, the guarantee that what was still is somewhere, somewhen, encoded forever in the architecture of space-time. This shifts our perspective on loss. It tells us that the people and places we love, the cultures and eras we fear to see vanish, are not erased by time. They are simply absorbed into it. Time is not a thief. It is a library. One that cannot be browsed in the ways we are used to, but which exists nonetheless, filled with volumes written in gravity and light. And frozen stars are the shelves upon which the most precious volumes rest. The thought is as chilling as it is comforting. For if nothing is truly lost, then we live in a universe that demands responsibility. If every choice, every action, every ripple persists, then we are not free from consequence, not even in death. We are permanent in ways we do not yet understand. We are archived even as we fade. That permanence is a burden, but also a blessing. It gives our existence weight. It renders our fleeting moments cosmic. And what greater meaning could there be? This understanding, that our universe is a place where permanence is embedded within impermanence, shakes the foundation of what it means to exist at all. To be is no longer just to inhabit a moment, it is to etch oneself into the space-time continuum in ways that resist erasure. We may live for a century, a civilization for 10,000 years, a star for 10 billion. But all of them, in one way or another, are inscribed into a geometry that does not forget. The very laws that govern frozen stars, the time dilation, the gravitational redshift, the limits of horizon formation, are expressions of the universe's commitment to preserving information, no matter how inaccessible it becomes. It tells us that reality is recursive, self-retaining, and fundamentally watchful, not because it sees, but because it remembers. When a massive star begins to collapse, it does so under the unyielding pull of its own gravity. To an external observer, that collapse slows down, asymptotically approaching a critical radius known as the Schwarzschild radius. In traditional black hole theory, once the star crosses that boundary, it disappears behind an event horizon. But in the frozen star model, that crossing never happens, not from our perspective. Instead, the star approaches its final state with infinite slowness. Time, warped by extreme gravity, slows so dramatically that what we see is a suspended process. A collapse frozen at the edge of completion. The star becomes an eternal transition, caught in a gravitational limbo where it is no longer quite a star, but not yet a singularity. This state, this in-between, might be the universe's most powerful tool for preservation. Because within this suspended collapse, matter doesn't vanish. It is still there. The atoms, the radiation, the internal processes, everything that once existed in the star remains, just drastically slowed down. To an observer falling into the star, time continues as normal. But to the rest of the universe, that journey stretches across infinite time. The surface of the star appears to freeze. And if that surface is just barely above the critical radius, then no true event horizon forms. The star never fully transitions into a black hole. It never becomes a region from which information cannot escape. Instead, it becomes an object where information can escape, just so slowly, so redshifted, that we haven't yet been able to detect it. But if we wait long enough, or build instruments precise enough, we might begin to see the signs. Subtle variations in the Hawking-like radiation emitted from these objects. Slight delays in the echoes of gravitational waves after mergers. Minuscule deviations from predictions made by the black hole no-hair theorem. These deviations could point to the existence of structure, surface effects, vibrations, thermodynamic behavior, impossible in a traditional black hole, but expected in a frozen star. They would imply that there is something there. A boundary. A skin. A place where physics doesn't end, but continues. And if there is a surface, then there is a way to read it. Reading a frozen star wouldn't be like reading a book. It would be like deciphering a language we don't yet speak, using senses we haven't yet evolved. The information isn't gone, it's just encoded into gravitational vibrations, redshifted electromagnetic emissions, and patterns in quantum fluctuations that span cosmic timescales. To us, they are noise. To a future intelligence, perhaps machine-based, or alien, or post-human, they may be legible messages. They may be stories, histories, scientific data. The accumulated memory of all things fallen in, stars, planets, spacecraft, thoughts. Not erased, but fossilized in time. And this leads to the greatest implication of all, that the universe itself may be structured as an information-preserving system. That reality is not just matter and energy, but a self-writing code, one that never deletes a line. Each frozen star becomes a chapter. Each galaxy a paragraph. Each fluctuation in the cosmic microwave background, a punctuation mark in a language we are only beginning to perceive. If this is true, then our universe is not heading toward meaninglessness, as some thermodynamic arguments have suggested, but toward compressed meaning, a state where all entropy is retained, but hidden. A state where everything is still there, simply inaccessible for now. In such a universe, collapse is not erasure. It is compression. Entropy doesn't destroy structure, it wraps it in more and more layers of translation, like a document zipped into a file format so dense we need millennia to unpack it. The frozen star is that zipped archive, a compressed record of everything that fell into it. And while we may not be able to decompress it now, the structure is still there. The data is intact. One day, it might be unpacked, reconstructed, understood. And this future understanding wouldn't just be scientific. It would reveal how stars lived, how civilizations died, how particles danced in the hearts of forgotten worlds. It would show us that the universe is not indifferent, but involved. Not because it cares, but because it records. The frozen star is the symbol of this involvement. It is the quiet reminder that the cosmos does not let go. So what do we do knowing this? We build accordingly. We speak accordingly. We live not just for the now, but for the trace. We begin to think of our actions as permanent, not ephemeral. Because they are. Every light switched on, every particle accelerated, every emotion, every decision, it is all encoded. Somewhere. In the air. In the dust. In the curvature. If not here, then there. If not in the mind, then in the metric. And perhaps that's all the afterlife we need. Frozen stars are not dreams. They are consequences. They are the logical endpoints of physics when carried to the extreme. And in their silence lies the answer to a million questions. Are we alone? Never. We are accompanied by the memory of all who came before. Will we be remembered? Always. If not by others, then by the structure of space itself. Is anything we do meaningful? Yes, because meaning is nothing more than what leaves a mark. And frozen stars are made of marks. So let us go forward with this knowledge, not with fear, but with reverence. Let us marvel not only at the vastness of space, but at its patience, its memory, its impossible slowness. Let us see frozen stars for what they truly are, not the end of things, but their long, deep beginning. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.